Okay, so I think it's about the time. So welcome to the second day of our summer school. So for the morning section, we have Professor Carpenter from Washington University in St. Louis to give us a lecture about this non-Hermitian system. So, so for the morning session, we'll have 2 breaks. And we'll divide the entire session into 3 lectures. So during the lectures, you are free to interrupt Professor Bender to ask questions. Okay, so if there's no problem, so let's welcome Professor Carpenter.
Okay. Professor Bender, you can start.
Okay, can you all hear me?
Yes, yes.
Okay, and can you also see my pointer here?
Yes.
Good. Okay. So, so I'm going to speak to you about PT symmetry, which is parity time symmetry. Let me say right away, thank you very much for your invitation to speak to you. And I should say, I wish I were speaking to you live. I'm not happy giving a talk sitting at my desk instead of standing at a blackboard, but that's what we're stuck with. So I hope you can, I hope you will not be too bored. So the idea of PT symmetry is simple. The idea is that we generalize quantum mechanics by replacing the mathematical condition of hermiticity, which is this, with a physically intuitive constraint of space-time reflection symmetry. So we're going to replace this condition with this condition, that the Hamiltonian is invariant under a reflection of space and simultaneously a reflection of time. Okay. And what you're going to see is that PT symmetry combines the fundamental concepts of quantum physics with the beautiful mathematical theory of complex variables. So that's the idea of this talk. And there are many research opportunities if you're interested in working on PT symmetry and you're interested in non-Hermitian quantum mechanics. Many people are working on it. This shows the number of publications. Okay, so PT symmetry is now 25 years old. And you can see the number of publications goes up and up and up and up, and it's rapidly increasing. By the end of this year, by the end of 2023, there will be more than 10,000 papers on PT symmetry, which is amazing. And if you want to see something about the PT research community, there are over 500 people who have published papers on PT symmetry. And this graph shows the connections, the people who are working together, the collaborations, okay? So I am over here, and these are the people who I have been working with, okay? But there are many other people. Christodoulides has written many papers on PT symmetry, and here are some of the people that he works with. Here's a guy named Alu, who's also worked very hard on PT symmetry. And you can see that there are many, many people. And this is only a small map of the community of people who are working on PT symmetry. So let me explain to you the theme of this talk. Mathematicians find it enlightening to extend the real number system to the complex number system, because it helps us to understand the real number system better. In this talk, what we are going to do is extend real physics to complex physics. And when we do this, we're going to find that we can understand quantization better. We can understand the divergence of perturbation theory. We can generate new PT symmetric quantum theories. We can tame instabilities. You're going to see that physical systems that look unstable are not unstable. And this is because of complex variable theory. And there's much, much, much more. And I won't have time to talk about a lot of things, but I hope you're going to get interested. And if you're not already interested in PT symmetry, and I hope you'll spend some time reading about it and learning more about it. Okay, so as you know, this talk is going to be organized in 3 parts. So this is the first part, and here is the second part, and here's the third part. Okay, so you know that the conventional world is described by real numbers. And you use real numbers if you want to report election results, for example, okay? Or if you would like to give your IQ test results, okay? Or if you want to talk about money, okay? So you use real numbers in that case. And indeed, here is a real quantity of money. In Brazil, the quantity of money is, you can see, it says right on their money, it says real. But complex mathematics is very, very powerful. And in many ways, it's more powerful than real mathematics. And it can explain many things. For example, it explains the convergence of real Taylor series. And it determines the asymptotic behavior of real integrals. And I will give you some examples. And it helps us to sum divergent series. And it explains real functions, such as the square root function, and much, much more, which maybe I will tell you about some other time. So let me give you some very simple examples of how powerful complex mathematics is. So let's take a very simple function. Let's take the function 1 over 1 plus x to the 4th, okay? If you make a plot of this function, this is what the function looks like. It's a simple, smooth function, and it's smooth for all values, all real values of x, okay? But here is the Taylor series for this function. And you notice that this Taylor series stops converging as soon as x gets bigger than 1 or smaller than -1. So the Taylor series is only good from about here to here. This is the only place where the Taylor series is good, even though the function is perfectly smooth all the way out to from minus infinity to infinity. So why is this? The answer is, as I'm sure you know, this function has singularities, but not on the real axis. The singularities lie in the complex plane, and the singularities are where this function blows up. And it blows up at 4 different places in the complex plane. For example, e to the I pi over 4. Okay? And this is the complex plane. And if I were to come and visit you, I think I would probably take this plane. This is my favorite plane. There's only one problem. I guess you can see it. There's one problem with this plane. The passengers ride over here, but the toilets are over here. And it's a very long ride to Taiwan. Okay, so complex variables are useful when you do asymptotic expansions of integrals. And here's a very good example. Here is a simple real integral. This integral converges. It defines a function which I'm going to call I of x. And we can ask, how does I of x behave when x is very large and positive, for example? Okay, so if x is very large and positive, you can see that this exponential is vanishing except near t equals 0. I hope you can all see that. And so the contribution when x is large and positive, the contribution to this integral comes very, very close to the origin. And since it comes very close to the origin along the t-axis, we might try to approximate this integral by saying, well, the only place you have a contribution to this integral is near t equals 0, so we can cancel this term over here. We don't have to care about this. And we might even consider canceling this term too, but if you do that, you get the wrong answer. And in fact, if you know how to find the asymptotic behavior of this integral for large positive x using only real variable calculus, you should publish a paper on this, because this is actually a very, very hard integral. Okay, now the answer, I'm telling you the answer, for large positive x, this integral has a very simple behavior. It behaves like an exponential of e to the minus 2x and the square root of pi over x as x goes to infinity. But the problem with the difficulty, I would say, with this integral is that for large x, the contribution is not localized at t equals 0. It's just not. And it is not localized over here on the real axis. So what you have to do, remember that's an integral from -1 to 1. What you have to do is to go into the complex plane. And instead of going from -1 to 1, what you do is you go from -1 out here to infinity. And then you come back from infinity and you pass through the point at I. And then you continue integrating to infinity over here in this direction, and you come back to 1. This is the complex plane, okay? And for large x, the contribution to the integral is localized at a saddle point over here in the complex plane at the point I. Okay, now if you have learned the saddle point method, you will understand what I'm talking about. And what I'm discussing here is the method of steepest descents. Okay, this is where the contribution to the integral is localized as x goes to infinity. It is not localized on the real axis, even though it looks like it is. This is a very difficult integral. You might, if you haven't seen this before, you might try working on it. Okay, now complex variables is also useful in summing divergent series. So here are 4 examples of divergent series. And each of these series has a finite sum. Okay, and I'm going to tell you what you get if you sum these divergent series. This is the answer. Okay, now you can sum this series and this series using techniques from real variable theory. But you can't sum this series or this series without using complex variable techniques. In fact, the sum of 1 plus 1 plus 1 plus 1 plus 1 and so on, that sum is equal to -1/2. And the sum of this series is equal to -1/12. And you might wonder, is this useful? And the answer is, it is very useful in physics, because we need to evaluate these sums in order to understand the Casimir force. Now, if you don't know what the Casimir force is, this is Professor Casimir, and he had a remarkable idea. He discovered the Casimir force, and this is his idea. If you have 2 parallel plates metal plates, and there is no electric charge on these plates. No electric charge, just two infinite parallel metal plates, okay? They will feel an attraction due to quantum mechanics. And why is this? The reason is that outside the plates, there are standing waves, and these waves extend to infinity. And over here, there are standing waves. And in between the plates, there are also vacuum fluctuations, which are represented by standing waves here. And now, what happens if we move the plates a little bit? If we separate the plates a tiny bit, these waves that extend to infinity will not change. And these waves that extend all the way to infinity will not change. But the waves in between the plates will change. And if you sum up the infinite number of energies in these waves, the 0-point energies, okay, now that sum looks like a divergent series, but you can use complex variables to sum those series. And in fact, you need to sum both of these series. You need to sum this series and you need to sum this series to calculate the Casimir force. But if you sum the series, you will find that these plates are attracted to one another, even though there is no electrical charge on the plates. Okay, that is called the Casimir force. And in fact, there's a very nice movie that I recommend you see if you have not seen it. And the movie is Indiana Jones and the Last Crusade. Okay, because in this movie, this is just an adventure movie, but in this movie, you will see a beautiful, dramatic example of the Casimir force. Okay, and in this movie, what you see is the good guy. This is Indiana Jones over here, and he is in a speedboat. And the speedboat is driven by his girlfriend, okay? And the bad guys are after Indiana Jones. They're in a boat behind Indiana Jones, okay? So he has his gun, but they have machine guns, and they're about to kill him. And what happens is the boat is going along, and they see two big boats in the water. Now, Indiana Jones knows about the Casimir force, and he knows that this boat is attracted to this boat, and those two boats will come together, okay? And he yells at his girlfriend, "Don't go between the boats." And his girlfriend can't hear him because the engine of the boat, the motor of the boat is too noisy. And she says to him, "Are you crazy? Because of the Casimir force, you should never go between the boats." Okay? And he says, "Don't go between the boats." And she thinks he said, "Go between the boats," because she can't hear him very well. And they do just get between the boats, but the boat that is chasing them blows up. And that's the end. That's how he escapes from his enemies. And it's all because of the Casimir force. And you know that if you speak with a sailor, someone who knows about boats, you never park two boats parallel to one another, because the boats will come together because of the Casimir force. Okay, so finally, complex variables helps us to understand real functions. And as an example, take the square root function. The square root function is very confusing because, as you know, there are two answers. Why are there two answers? Okay, so of course, here's one answer and here's another answer. But why is it that a function can have two possible values? You would think that's impossible. A function can only have one answer. Why is this? And the reason is that the square root function is defined on a Riemann surface. So a Riemann surface is two complex planes together, glued together, and it looks like this, okay? So there's one complex plane and another complex plane. And what you can see is that this is called a branch point. If you're on this complex plane, okay, and you go around the branch point, you are on the other complex plane. And if you continue rotating, you go down to the first complex plane, okay? So why are there two answers? It's because there are two complex planes, and if you go around twice, you come back to where you were, okay? So the square root of 1 is either +1 or -1, and that's because there are two sheets in the complex plane. So like a Mobius strip, if you go around twice, you return back to the starting point. Okay, and there are lots of things that remain the same when you go around twice. For example, a Mobius strip, except this is a Mobius strip stake. Okay, if you go around twice, you come back to the same point. But in physics, there's something very important, and that's an electron. If you walk around an electron 360 degrees, it does not look like the same electron. But if you go around a second time, it does look like the same electron. And I would like to give you a demonstration of that. Here's my cup of coffee, and I must be very careful not to spill the coffee. So what I'm going to do is I'm going to rotate to this cup of coffee around 360 degrees. Now watch me very carefully. I'm going around, 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 and around. And I've now gone 360 degrees, but it doesn't look the same because my arm is twisted and it hurts. So I'm going to go around another 360 degrees without spilling my coffee. I'm going to bring it around, around behind my head, back to where I start. And now you can see this is how I began. So if I went around once, that was not good. I had to go around twice. And I think this means that I'm an electron. Okay. So what I've done is I've tried to explain to you that complex variable theory is very important. And in fact, complex numbers are used all the time in modern physics, okay? But I want you to remember that complex numbers were not used until quantum mechanics was discovered. So in the theory of electricity, in the theory of fluid dynamics, sonics, all that does not use complex numbers. Even relativity does not use complex numbers. But modern physics, quantum mechanics does use complex numbers. And you can see this is the Heisenberg algebra. And here is the number I, okay? And this is a complex number that is fundamentally in the theory. And here is the Schrodinger equation. Don't look at the girl, okay? Just look at the equation, okay? And you can see in this equation, there's an I in that Schrodinger equation, okay? And Wigner explained to us that time reversal, T, time reversal, corresponds to complex conjugation. That is, time reversal means changing the sign of I. And you can see that in the Schrodinger equation. If you change the sign of I, that is exactly the same as changing the sign of T. Okay, now, when you learn quantum mechanics in school, you learn that in quantum mechanics, a particle in a potential well, so we're putting this particle in this potential well, and this particle has quantized energy levels, quantized, okay, quantized energy levels, and you learned that going from one energy level to another energy level is a discrete quantum leap. It's a jump. You go from one energy level up to another energy level, okay? But complex variable theory, complex analysis explains that much, much, much better, okay? And I'm going to show you a much more beautiful understanding of what is really happening when you talk about different energy levels. And as a very simple example, I want you to imagine a two-state quantum system having energies A and B. So it's described by this Hamiltonian. There's one energy A and another energy B, and these states are not interacting, okay? Now this guy over here is not smart enough to understand what I'm saying. He's not smart at all. He's a pretty stupid guy, but you understand what I'm saying, okay? So now what I'm going to do is I'm going to couple the states. So with a coupling constant G, I'm going to couple the state A with the state B, and this is my interacting Hamiltonian, okay? Now, if you want to know what are the energy levels of this Hamiltonian, you need to take the determinant of the Hamiltonian minus E, okay? Minus the unit matrix times E, the identity matrix times E. And if you take the determinant, you get this equation, and you set this equal to 0, and you find the roots, and you find that the energy, there are two energies, and this is the formula for the energies, okay? And you notice, you remember what I said before, I said that complex variable theory is very important in explaining the square root function. And you notice that this energy has a square root function in it. And the singularities, the square root singularities occur where the argument of this square root vanishes. That is, in the complex G plane, there are square root singularities in the complex G plane where this is 0. So that's where G is equal to the absolute value of A minus B times I divided by 2. These singularities are called Bender-Wu singularities. Well, that function is a smooth function defined on a two-sheeted Riemann surface. And this is what the Riemann surface looks like. These are those two singularities. And what you see is that on this complex coupling constant Riemann surface, the energy levels are not discrete. You don't have to make a quantum leap. If you're on sheet 1, which is one eigenvalue, and you want to go to the second eigenvalue, you can go smoothly, very smoothly around here to the second eigenvalue. So for this value of G, there are two answers. That's because when you have a square root function, there are two answers. So if you start at this energy level and you go around, you come to this energy level. And if you go around again, you come back to the first energy level, and you notice that there is not a quantum leap. It is a very smooth transition from one energy to the other energy. So on this complex coupling constant surface, the energy levels are not discrete. In fact, what you see is that quantization is topology. It's topological. What you see is that the quantized energy levels correspond to the discrete sheets in a Riemann surface. Each sheet, this sheet, or this sheet, the top sheet or the bottom sheet, corresponds to an energy level, okay? And furthermore, the square root singularities here, these square root singularities, explain why it is that if you calculate a perturbation expansion, why does that perturbation expansion diverge? It's because there are singularities in the complex coupling constant plane, okay? And these are the singularities, Okay, so if you were to expand this function into a series in powers of G, it would have a finite radius of convergence. Why? Because there are singularities here and here. The origin is over here. Okay? And furthermore, as I mentioned to you before, although I didn't explain it, complex variable techniques can be used to sum a divergent series. Okay, so in other words, he's not smart enough to do this, but you're smart enough. All you have to do is imagine a parking garage. You know, you drive into the parking garage and you drive around and around and around, and you go to a higher and higher level, and you notice it's smooth. There is no abrupt quantum leap from level to level. You can go smoothly from level to level to level in a parking garage, and that is what happens in quantum mechanics. Quantum mechanics looks like it's quantized in discrete energy levels, but only if you look on the real axis. So this is the real axis. If you cut this parking garage along this real axis, you say, oh, look at all these discrete energy levels. But they are not discrete. If you look in the complex plane, they're nice and smooth, and you can go around and around smoothly from one energy level to another. So unlike what is taught in conventional quantum theory courses, energy levels smoothly deform into one another under analytic continuation. You don't have a quantum leap. The energy is smooth, just like a classical system. And in fact, a quantum mechanical system behaves a lot like a classical system in the complex plane. Okay, now this sounds like mathematics, but it isn't. It's not mathematics. What I am talking to you about is physics. And in this paper, in Physical Review Letters, they were able to take a quantum system that is a microwave billiard, which has many, many energy levels, and they were able to smoothly continue from one energy level to the next. And an even better paper was published in 2016, and another paper in 2016, where this was done. These are papers published in Nature, okay? Beautiful, beautiful papers, where they were able to do this analytic continuation in a laboratory, okay? And I want you to notice something very interesting. You notice this term PT symmetry here, okay? And that's what I'm talking to you about. I'm talking to you about quantum mechanics in the complex plane, and I'm talking to you about PT symmetry. And that is the subject of my lectures today. Okay, so the question is, what is PT symmetric quantum mechanics? And I will say it very, very briefly. PT symmetric quantum mechanics consists of extending quantum mechanics from the real axis into the complex domain. And what I'm going to show you is that if you respect PT symmetry, the eigenvalues can remain real and unitarity can be preserved even if the Hamiltonian is not Hermitian. Okay, so what I want you to remember is that a PT reflection is a simultaneous reflection of space and time, okay? And this picture comes from a book. I'll show you the book. So here's the book. And if you look at the cover of the book, you can see that picture. This is a book on PT symmetry. And if you're interested, that book will give you a nice, easy to read introduction to the theory of PT symmetry. Okay, so let me give you an early example of a PT symmetric Hamiltonian. This is it, okay? This Hamiltonian is obviously not Hermitian, but it is PT symmetric. Why is that? Because if you do a space reflection, X turns into minus X and P turns into minus P. But under time reversal, X does not change sign, but P changes sign. And remember what Wigner said, I changes sign. So under PT symmetry, if you change the sign of I and you change the sign of X, the Hamiltonian remains invariant. So this Hamiltonian is not Hermitian, but it is PT symmetric. Now I have to tell you, when I first saw this Hamiltonian, someone showed me this Hamiltonian, and what I said, because I had a traditional education in physics, I said, this is stupid. I said, the way I see it, this theory is crazy. And I said that because this Hamiltonian is not Hermitian. And in my courses on quantum mechanics, I was taught that a Hamiltonian has to be Hermitian. Okay. However, a little while later, I noticed that in fact, this Hamiltonian has a symmetry. And the symmetry is that H remains invariant under I goes to minus I and X goes to minus X. Okay. And then I noticed that there's a very interesting way to explain PT symmetry from the point of view of relativity. Okay. So you remember that Newton discovered gravity. And you also remember that Einstein rediscovered it. He found an even better theory of gravity. So this is Newton sitting under a tree, waiting for an apple to fall on his head. And this is Einstein staring at a blackboard because he has just proved that time is actually money. And you know that's a very famous theorem of Einstein. Okay, so what does Einstein say? Einstein tells us that the Lorentz group is fundamental. And this is where complex variables comes in. So in your elementary physics course, you learned that the homogeneous Lorentz group is a 6-parameter group of real 4x4 matrices. Okay, and what do these matrices do? They transform the space-time point X, Y, Z, and T into X prime, Y prime, Z prime, and T prime. But they transform it in such a way that X squared plus Y squared plus Z squared minus T squared is preserved. This is a constant. Okay, so this is the light cone condition. Okay, and you know that there are some obvious elements of the Lorentz group. One of them is P and one of them is T. Okay, now what does P do? P changes the sign of X, Y, Z, and T, but not T. Okay, and time reversal leaves X, Y, and Z alone, but it changes the sign of T. Okay, so PT changes the sign of X and Y and Z and T. So it looks very nice from the point of view of the Lorentz group. Okay, now already we can see in the Lorentz group that there are complex numbers. In fact, Wigner explained to us that if you want to describe fermions, for example, if you have a 2-component spinner, that you have to use complex representations. But Einstein didn't know about that. He was just interested in coordinate representations, X, Y, Z, and T, a point in 4-dimensional space. Okay, now, if you look at a map of the Lorentz group, this is the Lorentz group, and the Lorentz group is a continuous group, but it falls apart into 4 parts. Okay, this is the proper orthochronous Lorentz group. And this is a subgroup of the Lorentz group. And it contains the identity. Okay, this is another part of the homogeneous Lorentz group, okay? These elements of the Lorentz group are all of these elements multiplied by P. And this is called, this is another part of the Lorentz group. It is all of these elements multiplied by T. And the fourth part of the Lorentz group are all of these elements multiplied by PT. Now, for many, many years, people thought that the natural world was invariant under all of the Lorentz group, all of these elements of the Lorentz group. However, as you know, Li and Yang, back in 1956, wrote a paper saying that it's not true, that in fact, these elements are not symmetries of nature, okay? And they won the Nobel Prize for it. And in fact, Madame Wu showed that they were correct in the laboratory. And you also know that Cronin and Fitch showed that these elements here are not symmetries of nature. They showed that time reversal is not, that the world is not invariant under time reversal, okay? So Li and Yang showed the world is not invariant under parity, P, and Cronin and Fitch won the Nobel Prize for showing that the world is not invariant under T. Well, this is the fourth part of the Lorentz group, okay? And these are all the elements of this group multiplied by PT, okay? So the question is this a symmetry of nature or not, okay? Now, if you extend the Lorentz group to the complex Lorentz group, then you see that there is a continuous path through group space from here to here. And so these two parts of the Lorentz group are linked in a natural way, in a beautiful natural way, if you look in the complex plane. Okay, also, this part of the Lorentz group is connected to this part of the Lorentz group in the complex plane. Okay, now, why is this important? Because if you are interested in reading a very difficult book, very highly mathematical book, very difficult, the name of the book is PCT, Spin and Statistics and all that. This is a book written by Streeter and Whiteman. And what they prove is a beautiful and powerful theorem in theoretical physics called the PCT theorem. And what they show is that if you live in the world, but you take another world that is reflected in space, that is reflected in time, and that is made out of antiparticles, C changes a particle into its antiparticle, those two worlds are indistinguishable. Experiments performed in this world and in this world are identical. They give identical results, okay? And this is a consequence of complex variable theory because you have to extend the real Lorentz group to the complex Lorentz group. So this is a very, very powerful theorem and it's very suggestive. But today we're not going to talk about particle physics. I'm only going to talk to you about elementary quantum mechanics. Okay, so the question is, how do you construct a PT symmetric Hamiltonian? And I'm going to give you a very, very simple recipe. You begin with a Hamiltonian that is both Hermitian and PT symmetric. Okay, so you begin with a Hermitian Hamiltonian that is also PT symmetric, and then you perform a PT symmetric deformation. And I'm going to explain to you what I mean, okay? But what I mean by a deformation is, for example, that you can add or multiply by a non-Hermitian but PT symmetric quantity like I times X. So this quantity is PT symmetric. So when you deform, when you continuously deform a Hermitian Hamiltonian by using a PT symmetric deformation, that Hamiltonian is no longer Hermitian, okay? But it is still PT symmetric. And this is because, remember, P replaces X by minus X, and T replaces I by minus I. And if you want to see some examples, this is a complex deformed squirrel, and this is a complex deformed frog. And here's a complex deformed bird, a parrot. Okay, so what is an example? Can I give you a very simple example? So let's take the harmonic oscillator. You all know what the harmonic oscillator is. And the harmonic oscillator is PT symmetric. It's Hermitian, of course, you know that. It is also PT symmetric because if you change the sign of P and X, because they're squared, this is invariant. So it is both T symmetric and P symmetric, okay? Now, notice that the eigenvalues of the harmonic oscillator are all real and positive. And these are the eigenvalues. Now, I'm going to deform this Hamiltonian by adding to the Hermitian harmonic oscillator something that is not Hermitian. And this is not Hermitian. You know, the term IX is not Hermitian. I'm going to put in a real deformation parameter that I'm going to call epsilon, okay? But what you will see is that the eigenvalues of this non-Hermitian Hamiltonian are still real and positive, okay? In fact, the eigenvalues of this Hamiltonian are given by this formula. And you notice that the eigenvalues are still real and positive. So we begin with one unique Hermitian Hamiltonian, and now we have an infinite number of non-Hermitian Hamiltonians, but they all have real positive eigenvalues, okay? And if you want to prove this, it's easy. All you have to do is write down the Schrodinger equation for this Hamiltonian and replace X by X minus I times epsilon, and you're done. Okay, and you can calculate these eigenvalues by yourself. It'll take you only 2 minutes to do it. Okay, so the eigenfunctions, of course, are complex, as in general, as eigenfunctions in general are complex, but they are still orthogonal. Okay, so we can take the position that PT symmetric Hamiltonians are fundamental, and a Hermitian Hamiltonian is just one special case of PT symmetric Hamiltonians. Okay, so
quick question.
Yeah.
When you compute orthogonalities, do you still use the Euclidean matrix in the vector space?
Yes, we're going to talk about that, and in fact, I will spend the last lecture today talking about what you mean by the inner product and how you define what is the equivalent of the, what is the adjoint of a PT symmetric Hamiltonian. And I will talk to you about that in general.
Thank you.
Okay. And we will derive I will explain how you define the PT adjoint, okay, to show that the theory is self-adjoint. Okay, we will talk about that. Okay, and that's going to be in the third lecture today. Okay, so just a comment before I stop. I'm going to stop in just another minute. So remember that we want the eigenvalues of a Hamiltonian to be real. Why is that? Because when you measure an energy in the laboratory, the result is real. Okay? Now, hermiticity is a very fancy mathematical condition. You know, in physics, when I define the axioms of quantum mechanics, all of the axioms are very physical. You know, I say positive probability. I say the spectrum has to be bounded below. Okay, I say that the ground state energy has to be stable. So stability, locality, these are all physical concepts. But one axiom of quantum mechanics is very, very mathematical, and it's not physical. And that's this condition, hermiticity. Hermiticity says if you take the complex conjugate and the transpose of your Hamiltonian matrix, you should get back the Hamiltonian matrix. That's mathematics. That doesn't sound like physics, okay? But hermiticity is a very powerful mathematical condition, and it does guarantee that the eigenvalues are real and also that the theory is unitary. But what I'm arguing today is that hermiticity is nice, but I don't like it because it's mathematics, not physics. And what I'm arguing today is that it is not a necessary condition. So what I'm going to show you in these talks is that there are infinitely many more PT symmetric Hamiltonians with real eigenvalues than Hermitian Hamiltonians. There are infinitely many more PT symmetric Hamiltonians. So the Hermitian Hamiltonian that I just showed you is just one special case, and it's not very different from all the other Hamiltonians. And what I was saying to you before was we might adopt the view that PT symmetry is a fundamental physical property. It's a physical condition, and it's a physical property of a quantum Hamiltonian. And hermiticity is just a simple special case. Okay? So when I begin my next lecture, I'm going to talk to you about how you prove that the eigenvalues of a Hermitian Hamiltonian are real. And we're going to look at some very fancy examples of PT symmetric Hamiltonians. Okay, so I think we should stop now and take a short break. Okay, and then in 15 minutes, I will begin again.
Okay, so then, can we just ask questions if anyone here has questions?
Yeah.
Okay.
So PT symmetry is it somehow related to the supersymmetric quantum mechanics?
Is it you're asking if PT symmetry is related to supersymmetry? Is that what you're asking?
Quantum mechanics.
In quantum mechanics?
Yeah.
Yeah. So the answer is no. PT symmetry is not the same as supersymmetry. However, it is interesting that you can take a supersymmetric Hamiltonian and make it PT symmetric without destroying the supersymmetry. So there are a number of papers written on that, and you can look them up. I can mention them to you. So you might think that if you begin with a supersymmetric Hamiltonian and you then make it PT symmetric, you might think that this would destroy the PT symmetry. I'm sorry, that it might destroy the supersymmetry. Okay, you might, that PT symmetry might interfere with supersymmetry, but it doesn't. In fact, PT symmetry is compatible with supersymmetry. They don't interfere with each other at all. You can have a supersymmetric, PT symmetric Hamiltonian, no problem.
So the question is this PT condition, is it necessary and sufficient to have real eigenvalues?
You are asking, I think you asked, I couldn't quite hear you well, but I think you were asking if you have PT symmetry, will the eigenvalues be real?
Yes. So is it sufficient condition?
Right. So you're asking me, does PT symmetry imply that the eigenvalues are real?
Yes.
Is that correct?
Yes.
And the answer is no. So if you have a Hamiltonian that is Hermitian, you know that its eigenvalues will be real. If you have a Hamiltonian that is PT symmetric, the eigenvalues may be real, but they may not be real. Okay, so this is what I'm going to talk about at the beginning of the next lecture, and I'm going to show you that that if you have a PT symmetric Hamiltonian, the eigenvalues are either real or they come in complex conjugate pairs. So they can be complex, okay? If the eigenvalues are all real, we say that we have an unbroken PT symmetry. And if the eigenvalues of a PT symmetric Hamiltonian are complex, then we say we have a broken PT symmetry. And there is a transition between a broken PT symmetry and an unbroken PT symmetry, okay? And usually at the transition point, that is where the Hamiltonian is Hermitian, okay? So Hermitian Hamiltonians are at the transition between broken PT symmetry, where the eigenvalues are complex, and unbroken PT symmetry, where the eigenvalues are real. And I'm going to talk to you about that in just a few minutes in the very next lecture.
Thank you. Okay, so I think let's take a break. So we'll come back at 10:05. Yeah.
Okay. Are you able to understand what I'm saying? Am I speaking clearly enough?
Very clear, I think. Yeah, very clear.
Okay, so you're okay with the speed that I'm going at?
Yes, yes, yes.
Okay,
Okay,
good.
yes.
Okay, so I will be back in just a moment.
Okay.
Okay.
Gotcha.
Okay, good. Okay, so shall I start the second lecture?
So before that, can we just ask anyone here has any question before we move on? So, so we have one more questions. Can we take that up?
It's well known that in 2+1 dimension, Dirac fermion actually violate parity symmetry. I wonder whether it is PT symmetric.
That's a good question. I suspect the answer is yes. But it's also Hermitian, you understand. So, you know, if you have a Hermitian theory, it's perfectly possible for the theory to have PT symmetry, okay, such as the harmonic oscillator. Okay, so what is, I think, more interesting is that if you have a non-Hermitian theory, but the theory is still PT symmetric. Okay.
Okay, thank you. So I think let's move on to the second part of today's lectures.
Okay, so this is something that if you have had an elementary quantum mechanics course, you learn very quickly. You learn that how to prove that the eigenvalues are real if you have a Hermitian Hamiltonian. Okay, so how do you do that? You write down the Schrodinger equation in quantum mechanics, and this is just a Schrodinger equation with a potential, and it's in one dimension, okay? And all you do is you multiply by psi star, and you integrate from -infinity to infinity, and you integrate the first term by parts. And if you do that, the minus sign changes into a plus sign here. And this is what you have, okay? And then you notice that this is real, and this is real if the potential is real. And therefore, since this is real, the energy must be real, okay? So if the potential is real and the Hamiltonian is Hermitian, the energy is real. And this is, you know this from elementary quantum mechanics, but I want you to notice that we used integration by parts. And that means that self-adjointness, which is non-local, is more powerful than hermiticity, which is local, okay? So when you say a Hamiltonian is Hermitian, really that's a local condition. You can just look at a Hamiltonian and in your mind, you can just take the complex conjugate and transpose, and you know right away that the Hamiltonian is Hermitian, okay? But if you actually want to prove that the eigenvalues are real, that's not enough because you need to integrate by parts, okay? Unless your Hamiltonian is just a matrix. If it's a matrix Hamiltonian, of course, you don't need to integrate by parts. But if you have a Hamiltonian in physics, which involves space and you have to integrate, remember that you actually, hermiticity is not enough. You really need self-adjointness. So don't forget that. That's a much more powerful condition because it's non-local than just hermiticity, which is local, okay? Now, let me give you a wrong proof that if you have a PT symmetric Hamiltonian, the eigenvalues are real, okay? So listen carefully and try to see if you can find the mistake in my proof, okay? So we write down the Schrodinger equation, okay, the time-independent Schrodinger equation, and we remember that PT commutes with the Hamiltonian because it is PT symmetric. And remember that you learned a theorem in your elementary quantum mechanics course that says that if you have an operator that commutes with the Hamiltonian, they are simultaneously diagonalizable, okay? You understand what that means? So if I have a Hamiltonian which is parity symmetric, that means that parity commutes with the Hamiltonian. And that means that all of the eigenstates of the Hamiltonian are also eigenstates of parity. And so the eigenstates, for example, of the harmonic oscillator are either even parity or odd parity, but they have definite parity. And that's because they are simultaneously diagonalizable, okay? So remember that theorem. So now let's take this equation here, okay? So we assume that PT commutes with the Hamiltonian. And if it commutes with the Hamiltonian, an eigenstate of the Hamiltonian must also be an eigenstate of PT, right? So we take this equation and we multiply by PT, and we remember that P and T commute with each other, okay? So if I multiply this equation by PT, I get PT squared, which is 1, and I get PT times lambda times psi, okay? But remember, T does complex conjugation. So if I move PT past lambda, I get lambda star. And then when PT acts on psi, I get lambda again. And so that shows that psi is equal to lambda star lambda times psi. Okay, and that proves that lambda squared is 1. Okay, so that proves that the eigenvalues of PT lie on a circle in the complex plane. That is, we have proved that the absolute value of lambda is 1. Okay, and that's a true theorem. I did not make a mistake there. Okay, well now all we need to do is take the top equation, the Schrodinger equation, and multiply by PT. Now look what happens. If I multiply here by PT, I can commute PT past the Hamiltonian, and when PT acts on psi, I get back lambda. Now over here, I multiply by PT, I commute it past psi, and that gives me E star. But PT acting on psi is lambda again. And this shows me that lambda is not 0. In absolute value, lambda is 1. So we divide both sides of the equation by lambda, and we're left with the equation E equals E star. So it looks like I proved to you that the energy is real, E equals E star, and this is wrong, okay? So in this proof, I made a mistake. Can you see where I made the mistake? Okay, this is a nice proof, but it's completely wrong. So the reason that the proof is wrong is that I said to you that if PT commutes with H, they are simultaneously diagonalizable. And that is not true. It's only true if PT is a linear operator, but PT is not a linear operator because T, time reversal, takes complex conjugation. So it's antilinear, it's not linear. Okay, so this is a wrong theorem. Okay, so we do not have a general theorem that says that the eigenvalues have to be real. They could be complex. So they might be real or they might be complex. Okay, so this proof is wrong because PT is a nonlinear operator. All we can say is that the secular equation for the eigenvalues is real. Nevertheless, the beautiful and amazing fact is that even though we cannot prove it in general, the eigenvalues are often real. Even though they're not always real, they're often real, and that's an amazing result. Okay, and I'm going to give you a very non-trivial result, and this is a paper that I wrote with my student Becher 25 years ago. And what we did was we looked at this Hamiltonian. So what we did was we took the harmonic oscillator, p squared plus x squared, and we did, instead of an additive deformation, we did a multiplicative deformation. We multiplied, we didn't add ix, we multiplied by ix to the power epsilon. And this is what we found. We found that, of course, if epsilon is equal to 0, then the eigenvalues of this Hamiltonian are the eigenvalues of the harmonic oscillator. So this is epsilon, and at epsilon equals 0, here are the eigenvalues of the harmonic oscillator, okay? And as epsilon increases, look what happens. All of the eigenvalues remain real. So for positive epsilon, the eigenvalues are real. For negative epsilon, something funny happens. The eigenvalues come together, the real eigenvalues come together, they come together at a point and they disappear. Okay? Now, of course, the eigenvalues have not really disappeared. What has happened is that these two eigenvalues have gone off into the complex plane. Okay? But for positive epsilon, the eigenvalues are all real. For negative epsilon, the eigenvalues can be real. You notice these are real eigenvalues, but the rest of the eigenvalues are complex, okay? And this is very interesting because suppose I take epsilon equal to 2. If I take epsilon equals 2, the Hamiltonian is p squared minus x to the 4. Do you see why it's minus? It's because I squared is minus 1. So this is an upside down potential. And what I'm telling you today is that this upside down potential has real positive eigenvalues. Look, here's epsilon equals 2, positive, 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 positive. How can an upside down potential have real positive eigenvalues? And I will explain that to you very shortly. Okay, and that's very interesting because now, 25 years later, we have published a paper in Physical Review Letters explaining how to use cold atom experiments to observe these positive eigenvalues. Okay, we can actually observe them in the laboratory, and we have proposed this experiment in Physical Review Letters, and this Physical Review letter appeared just a few weeks ago. Okay.
So can I ask a quick question?
Sure.
So can I understand this epsilon as some kind of perturbation, or maybe I should think of it as a singular perturbation?
Yes, it is a perturbation. So we are perturbing the harmonic oscillator, not with an additive perturbation, but with a power perturbation. The small parameter is in the exponent, and this is deforming the quantum harmonic oscillator into the complex domain. So this is a continuous, smooth deformation, and this epsilon can be treated as a perturbation parameter, and we can do perturbation theory in powers of epsilon. We can write down a perturbation series, and all of the coefficients in that perturbation series are real.
But the part that I'm a little bit confused is you mentioned that when epsilon is negative, something strange is happening, right?
Yes.
And
yes.
that seems to be some kind of signal that at epsilon equal to 0, the behavior is very different. So does that mean like it is a singular perturbation or something?
Exactly. You're exactly right. Very, very good. Epsilon is not a regular perturbation. It is a singular perturbation. And the physics changes abruptly. Okay, so for positive epsilon, you will see that we have real energies, but we also have the eigenstates are orthonormal. Okay, and we have a the inner product of two of the states for positive epsilon. If we take the state into itself, we get a positive number. But when epsilon is negative, that's not true.
I see. Thank you.
Okay. So that's a very good question. Thank you. Okay. And this is an even more detailed, more careful graph. You can see all of the eigenvalues are real and positive and discrete for positive epsilon. But for negative epsilon, they come together in pairs and they become complex.
Question.
Okay.
Question.
Yeah.
What is the domain of your wave functions?
Oh, I'm going to tell you about that. So if epsilon is less than 1, the domain can be the real axis. But if epsilon is greater than 1, the domain is in the complex plane, and you will see that. Okay.
Yes.
All right. So just to show you how general this is, I'm not going to take just this. Hold on. I'm not going to just take x squared times ix to the epsilon, but rather I'm going to take a much more general theory. I'm going to take p to the 2m, not just p squared, but p to the 2m. And I'm going to add to that x to the 2n, and I'm going to multiply that by ix to the epsilon. And you notice that if epsilon is positive for various values of m and n, the eigenvalues are all strictly real and positive and discrete. Okay? So this is a very, very, very general theory that I'm presenting to you, extremely general. This is an infinite class of quantum theories, quantum mechanical theories. Okay, so if you want to see more, what happens when the eigenvalues come together? What happens is that the real part of the eigenvalue continues on, and just as you approach -1, it blows up. Okay, but just as the two eigenstates, the two eigenvalues come together, the imaginary part, which was 0 until now, the imaginary part of the eigenvalues is non-zero. One eigenvalue has a positive imaginary part, and the other part of the other eigenvalue has a negative imaginary part. Okay, now you can ask, has this been proved that these eigenvalues, when epsilon is positive, has it been proved that the eigenvalues are real? Yes, it has. There is a very fancy, difficult proof of the reality. I'm going to show you a simple proof later on for a special case. But this is a general proof, and the proof was given back in 2001. It took 3 years for somebody to discover this proof. This is a beautiful proof. This is a review paper, which you can read if you're a mathematician and you're interested in mathematics. And by the way, this is called the broken region, as I said before, because the eigenvalues are not all real. Some of them are complex. And this is the unbroken region because all of the eigenvalues are real. Okay, so don't forget, this is the broken PT region, and this is the unbroken PT region, okay? Okay, so what I would say to you is Hermitian Hamiltonians are boring. Why are they boring? Because the eigenvalues are always real. Nothing interesting happens, okay? So everybody here is going to sleep, including this guy. Do you know who that is? That's our President Bush, okay? And when he's giving a speech, his daughters, these are his daughters are going to sleep. Okay, but PT symmetric Hamiltonians are astonishing. Why? Because there is a transition point between regions of broken and unbroken PT symmetry, and you can observe this in the laboratory. It's very easy to observe this experimentally in the laboratory, and that is a really beautiful and wonderful thing, okay? So all these people are surprised about the fact that there is this beautiful transition between broken and unbroken PT symmetry, okay? And I'm going to give you an intuitive explanation of the PT transition. And you can see this is the PT transition, Putin and Trump. Okay, so to understand the PT transition, I want you to imagine a closed box with gain. That means I'm putting stuff into this box, okay? It doesn't matter what I'm putting into the box. I could be putting water into the box. I could be putting energy into the box. I could be putting photons into the box, elementary particles. It doesn't matter which. But if you want to describe a box with stuff going into it, this is a very simple system, and you can describe it by a 1-by-1 matrix Hamiltonian. And if B is complex, the sign of B is important, because for one sign of B, the stuff in the box decays, that's radioactive decay. And for the other sign of B, it increases. And that is what you see here. Stuff is going into the box, and the wave function inside of the box, the absolute value of the wave function in the box is growing exponentially in time, okay? Okay, now let's take two non-interacting boxes, okay? We're putting stuff into this box, but we're taking stuff out of this box. It doesn't matter what it is, but we're putting stuff in here and taking stuff out here. So now we have, the boxes are not interacting. So we have a 2-by-2 matrix Hamiltonian. Here the stuff is going in, and here the stuff is going out, okay? Now this system is not an equilibrium because this box is getting filled and this box is becoming empty. So this is not an equilibrium system. It's changing in time. Okay, but now look what I do. I'm going to connect the boxes. If I connect the boxes with a pipe, look what happens. Water is going into this box and trying to fill up this box, but it is flowing through this pipe into this box, and I'm taking water out of that box. So if I put water into this box, it flows through here and I take it out of this box. Now the system can be in equilibrium if it's easy for the water to flow through this pipe. Okay, so what I've done is I've taken the Hamiltonian and I've coupled the Hamiltonian with a coupling constant G. Okay, now this Hamiltonian is not Hermitian, but it is PT symmetric. Why is that? Because time T is time reversal, which is complex conjugation, and parity is just this real matrix. All parity does is it interchanges the boxes. So you can see that this system is PT symmetric. Why is that? Because under parity, I interchange the two boxes. But under time reversal, what is going in is going out, and what is going out is coming in. So that's an invariance of this physical system. And this physical system can be in equilibrium, and if it's in equilibrium, it can have real eigenvalues.
Can I ask a quick question?
Sure.
So I'm not sure whether I should try to understand that in the Hermitian language, but I'm a bit confused. So for this box state, it is not really a static state as in the Hilbert space of a Hermitian system, right?
Right. That's right. So we have
some time dependence, something like that.
So what this means is that we are talking about a state that is not static, but it is in dynamic equilibrium.
I see. I see.
So if I put stuff in here and I take stuff out of here, then my brain is in dynamic equilibrium, but it is not static.
I see. So that's a very different situation compared with the conventional Hermitian system, right?
Exactly.
So the basis is completely different.
That's right.
So the Hilbert space is also different because it doesn't guarantee that these two states are...
The Hilbert space has the same basic structure, but you are completely correct that there's a difference between static equilibrium and dynamic equilibrium. And let me just say to you that dynamic equilibrium is much, much more interesting.
I see.
Okay, and you're going to see why. You're going to see a lot of examples. Okay.
Okay, thank you.
So if I take this Hamiltonian and I look for its eigenvalues, okay, I take the determinant, I get a quadratic equation. This is the energy. And you notice that if G squared is bigger than B squared, the energies are real. But if G squared is smaller than B squared, this is negative. And when I take the square root, the energies are complex. Okay, so there's a transition at G equals B. So the system is in equilibrium for sufficiently large coupling. And that means simply that if this pipe is wide enough so that the water can easily flow through the pipe, then this makes the system, it puts the system in dynamic equilibrium. If this is a very thin pipe, it's not good enough to balance the water going in and the water going out. Okay, you see that? And the water going in and going out is measured by B. So what you see is that G must be bigger than B in order to have dynamic equilibrium. Okay, so remember that PT symmetry means balanced, loss, and gain. Okay, so what I did was I went on to ChatGPT. okay? And I asked ChatGPT to write a poem about PT symmetry. And in a fraction of 1 second, much faster than 1 second, ChatGPT wrote this poem about PT symmetry, and I'm going to read it to you because it is unbelievably clever. Okay, so what it says is, in realms unseen where quantum whispers speak, a novel symmetry doth enter stage, with parity and time, a dance unique to bind the quantum actors, new age. The PT symmetry, a twofold guise, where P reflects space, yet T and time, together sing a tale of compromise. In quantum world, a balance. Did you hear that? A balance most sublime. Unbroken, this domain of spectral dance, the loss and gain of energy entwined, their quantum states, a harmonizing trance, in eerie beauty to each other bind, and thus, in deep embrace of mystic schemes, PT symmetric quantum magic gleams. Okay? And this is written in Shakespearean language. So this may be a little bit harder for you to understand these words, but this is the way Shakespeare used to speak. And it is amazing that ChatGPT knows all about PT symmetry because it's read millions, well, not millions, but thousands of papers on PT symmetry. Okay, so PT symmetric systems are new because they lie between closed and open systems. So in your studies of quantum mechanics, you have studied closed systems, which can be Hermitian and have real eigenvalues. And you've also studied open systems, and you've learned that open systems are systems where stuff is going in and stuff is going out, as in a scattering experiment, okay? And these are generally described by non-Hermitian Hamiltonians. But what we are talking about is something in between. So we have a system that is not closed. The water is going in and the water is going out. So it's a dynamical system, okay? But the energies are still real, like the energies of this system, okay? And you see this guy over here, he's very excited about PT symmetry, and so am I. So I'm going to show you how excited I am. Okay, so now you know I'm very excited about it. And this is where the PT symmetric Hamiltonians are, okay? Okay, so I'm going to mention some beautiful experimental work on PT symmetry that inspired many of the papers on PT symmetry. So remember, I wrote my first paper in 1998, okay? And about 10 years later, this paper appeared where they observed the PT transition. That is, they saw the transition from complex eigenvalues to real eigenvalues, and they used optical waveguides. And you can read this paper. It's a very easy paper. And if you're interested in seeing the experiment, this is the experiment. It's a very simple laboratory. This is just a table in the laboratory, okay? And this is the optics experiment. This is a very short paper I wrote in Europhysics News back in 2016. And this is a picture that I took. So I visited the laboratory where the experiment was done, okay? And I took this picture, and this is a very, very, very simple optics experiment, okay? And you can read about the experiment. And by the way, in 2015, you might find this interesting, in the journal Nature Physics, which is a very important journal in physics, there was a cartoon, and the cartoon, it's funny, but it's a serious cartoon. And then the title is The Top 10 Physics Discoveries of the Last 10 Years. Okay, and there are little jokes, of course. They talk about the discovery of the Higgs boson, but you notice they spelled it wrong. They called it the Higgs bison. This is a bison. Okay, so they made jokes out of all the experiments by misspelling the words. And here, as one of the top 10 discoveries, they talked about party time symmetry in optics, party time, okay? And that's because they left off the I, not parity time symmetry in optics, but party time symmetry, okay? So here are some people dancing at a party, okay? Okay, and PT symmetry has become very popular even in China. So I was at a conference in China where they were interested in PT. They had the whole conference on PT symmetry. If you're Chinese, you might not see the reference to PT here. I don't know if you see it. Do you? I'll help you. Can you see it now? Okay, so this tells you where the toilets are, and this tells you where the PT symmetry is. Okay, so after they published that paper in Physical Review Letters, they wrote an even better paper in Nature Physics. This is a beautiful paper on the earliest optics experiments on PT symmetry, where they observed the PT transition from broken PT to unbroken PT. Okay, and you can read this paper. It's a very beautiful paper. Okay, and in that paper, they do a very simple experiment. What they do is this. They have light going through an optical fiber. So this is a light beam going through here, and another light beam going through here. Okay, now what they do is they shine a laser on this optical fiber, and by shining the laser, this light beam becomes brighter. So this light beam has gain. Light is flowing into this fiber. But what in this fiber, they have metal, and metal tends to absorb light. So this has loss. The light is disappearing, but the light can flow because these fibers are touching. Some of the light can flow from here to here. So do you remember the boxes? Okay, so we have light going in, light flowing from one box to the other box, and light going out. And this is a PT symmetric system. And they observe the PT transition between broken and unbroken PT symmetry. It's a beautiful experiment. Okay, so this is the Hamiltonian for one fiber. This is the same thing that I just told you before. You now have two uncoupled fibers. Here we have two coupled fibers. And this Hamiltonian is, as I said to you before, it's PT symmetric. This is parity. Time reversal is complex conjugation. And here is the secular equation. And the energies are real if the coupling of the fibers. That is, if the light can flow from one fiber to the other fiber easily, and then you have an unbroken PT symmetry. Okay, so there are two regions, by the way, of unbroken PT symmetry. There is G greater than B and G less than minus B. Okay, and in between, there's a region of broken PT symmetry where G is smaller than B, but bigger than minus B. And in the region of unbroken symmetry, the system is in dynamic equilibrium, okay? Okay, so we're taught that there are two types of quantum systems: open, which are connected to the environment, and closed, where the system is not connected to the environment, it's isolated. And PT systems are new because they are connected to the environment, but the energy is conserved. And that's a really interesting new system that you can study mathematically and you can study in the laboratory. Okay, so just in case you're interested, there are two things in my personal background which led me to discover PT symmetry. One of them is that I have studied perturbation theory at a very deep level. And I'm interested in the questions of why perturbation series diverge and how fast it diverges. And these are, many people have written papers on this, Dyson, Hurst, Turing, Pitterman. And this involves level crossing, exceptional points, and so on. But I'm also interested in developing new kinds of perturbation techniques, and in particular, exponential perturbation theory, which I showed you before. Okay, so an example of exponential perturbation, let me give you a very simple example. In physics, there is an equation called the Thomas Fermi equation. Okay, and this is a semi-classical description of a nucleus of an atom. Okay, this describes the charge density, the electric charge density in a nucleus. Okay, it's high in the middle and it goes down as you go away from the center of the nucleus. Okay, so this is the equation that describes this curve. And the boundary conditions are that at 0, this curve is 1, at infinity, it is 0. And although this looks like a pretty simple differential equation, nobody knows how to solve this equation. However, you can solve this equation by using exponential perturbation theory. So all you need to do is, instead of studying this equation, let's study this equation here, okay? And we're interested in this equation when delta is equal to 1/2. And you can solve this equation perturbatively very easily by developing a series in powers of delta. And of course, I like to call it epsilon, but I'm calling it delta for this problem. Okay, and if you do a third order calculation, you can calculate the results accurate to better than, to 1% easily. So it only takes you a few minutes and you can solve this problem very, very accurately. Okay, so the question is, does that idea work in quantum mechanics? Well, for example, could you take the anharmonic oscillator, which you don't know how to solve, and write that as the harmonic oscillator times x squared to the delta? Okay, and if you let delta go from 0 to 1, you get the anharmonic oscillator, and you could expand in powers of delta, and that gives you a accurate numerical calculation. But after looking at this, it gave me a very interesting idea. Instead of raising x squared to the delta, let's raise ix to the epsilon. And this took several years of thinking, but finally, this is where PT symmetry comes from. And it's interesting, as you know, that this Hamiltonian is not Hermitian, but it is PT symmetric. Okay? Now, you have to understand that this is a remarkably complicated Hamiltonian, because if we're talking about a minus x to the 4 potential, how can it have positive eigenvalues? And I'm going to try to explain this to you in the next few minutes. Okay? So how do we make a minus x to the 4 potential? How do we do that? So one way to do it is to say, let's write down g x to the 4, and let's rotate g in the complex plane. So I will start with positive g, and I'll just rotate G in the complex plane until G is negative. If we do that, we wind up with a theory that has complex eigenvalues, unstable states, and it is an unstable potential. It doesn't have bound states, okay? On the other hand, we can make a minus x to the 4 potential if we take x squared and multiply by I x to the epsilon and let epsilon go from 0 to 2. Now, again, we end up with a minus x to the 4 potential, okay? But doing it this way preserves PT symmetry. In this technique, we do not have a PT symmetric Hamiltonian. We violate PT symmetry. But if we do this, we maintain the PT symmetry for all values of epsilon. And as a result, we end up with real eigenvalues. And in Dyson's studies of perturbation theory, Dyson never thought of this. So Dyson always felt that an upside down potential was unstable. And he didn't realize that you can make a minus x to the 4 potential in 2 ways. You can change the sign out front, or you can multiply by ix to the epsilon. And although the Hamiltonian looks the same, the boundary conditions are different, okay? So Dyson didn't realize this. And in fact, I traveled to Princeton. So Dyson and I were good friends for many years. And I had a long discussion with Dyson, and he said, yes, you're right. So I felt very good. Okay, so what I'm telling you is that the Hamiltonian p squared minus x to the 4 represents 2 completely different theories. One theory has unstable states, complex energies. The other theory, for the same Hamiltonian, has real energies. And the question is, how could you possibly have stable states with real energies if you have an upside down potential? And I'm going to explain that to you now, just at the end of this lecture, okay? So how can we have unstable states and stable states? How can this be? Okay, so I want you to notice what happens as we increase epsilon. Okay, so if epsilon equals 0, here's epsilon equals 0, this is the harmonic oscillator. And the harmonic oscillator eigen functions vanish on the real axis as we go to plus infinity and minus infinity, but they also vanish in the complex plane here if you go to infinity inside of this wedge, and also if you go to infinity inside of this wedge. Now, what happens is that if you increase epsilon to 1, the wedges rotate down. Okay, so this wedge rotates downward, and this wedge rotates downward. And if you increase epsilon to 2 and you make a minus x to the 4 potential, the wedges look like this. So you asked me this question before, and now I'm explaining the answer. The answer is that the eigenfunctions have to vanish in the complex plane like this. They have to vanish in this direction, anywhere in this direction, and anywhere in this direction. Okay? If you look at the other kind of upside down potential, the eigenfunctions vanish in this direction and in this direction. That's not PT symmetric. PT symmetric means left-right symmetric. Okay, why is that? Because under parity, x over here goes to minus x, and under time reversal, x goes into x complex conjugate. So PT symmetry means left-right symmetric in the complex plane. So complex conjugation means up-down symmetric, and PT symmetry means left-right symmetric.
The section also depending on epsilon?
Yes, I mean, the wedges depend on epsilon. as you increase epsilon, the wedges change.
Looks like shrinking.
Yes, they are shrinking. So yes, you're absolutely right. So as epsilon goes to infinity, this wedge is infinitely thin and it lies along the negative axis. And this wedge is infinitely thin and this also lies along the negative axis, okay? And this is the one case where you can solve a PT symmetric theory exactly. This is the PT symmetric square well.
So
Okay,
can I ask
so,
a simple question about how X transform? I think I maybe missed something very simple. You mentioned that time reversal symmetry will send X to X conjugate?
no.
No, I misunderstood.
Parity
Okay.
symmetry sends X into minus X. So if I have a complex value of X, say over here, any complex value of X under parity, it goes over here.
Ah, I see. Sorry, I think I just misheard you. Yeah.
Right. And then time reversal sends X into its complex conjugate down here. So if you start here, parity takes you here, time reversal takes you here. So PT takes you from right to left.
I see. So here the X, I should not understand it as the, position operator or something. I should understand that.
You can think of it as the position operator, or if we're in coordinate space, the position operator is just X. Okay, so I'm writing down the Schrodinger equation in coordinate space. So it sends X into minus X. That's all.
Okay, so maybe something I'm a little bit confused. So usually when I have a coordinate in real space, my objects just sit there, and I just unwind my time. And if that object is static, it just sit there still. So why I get a complex conjugate of that? Like,
I'm showing you what happens if you take a symmetry transformation on a Schrodinger equation.
Okay.
I'm talking about a symmetry condition on X. Is that okay? I'm asking, if I have an equation that contains X, I can ask what happens if I replace X by minus X?
Yes.
That's a symmetry.
Yes.
Okay.
And
another symmetry is to replace I by minus I. That's another symmetry.
I see.
Okay. So the Schrodinger equation may remain invariant under X goes to minus X and I goes to minus I.
I see.
So the physics is PT symmetric in that case.
I see. Okay, thank you.
In this case, these are the boundary conditions on the Schrodinger equation. Okay, so maybe before I answer, let me just give you a very quick explanation. Before I quit, I want to give you this explanation of why it is that an upside down repulsive potential can have a real spectrum. And it's a very simple argument, okay? It's very surprising. She is very surprised, okay? How can an upside down potential have a real positive spectrum of bound states? How is it that I can push things away and they are bound? How can that be? It's amazing. And I'm going to show you that it's true. Okay? And it's a very simple argument. So this is, so the question is, if my potential is minus x to the 4, this upside down potential looks unstable on the real axis. But complex variable theory explains why there are quantum bound states. And this is very interesting, okay? And I'm going to give you a clue, okay? So to understand what is going on, let's take a classical particle in an upside down quartic potential, okay? So this is an upside down quartic potential. And I'm going to study this not quantum mechanically, but classically. So I'm going to write down the equations of motion, Hamilton's equations of motion, and you know what you learned in elementary mechanics. You learned that the time derivative of x is dh dp, which is 2p, okay? And you learned that the time derivative of p is minus dh dx, which is 4x cubed, okay? So therefore, if I simply substitute this p into the Hamiltonian, and remember that the Hamiltonian is the energy, I get this equation. So this is a first order equation because I take the square root, okay? So p is equal to the square root of e plus x to the 4, right here, okay? Now, this is a first order differential equation. It's easy to solve. I multiply by dt, I divide by the square root of e plus x to the 4, and I integrate, and the integral of dt is time, t. And this is the integral over x, okay? And so if I ask, how long does it take for x to go from 0 to infinity? How long does it take for a particle to go to infinity? It takes this amount of time. Okay, and you can do this equation, you can do this in general for an x to the n potential, it doesn't matter. And what you find is that there's a critical value if the power is, if the power of x is 2, okay? So if epsilon is greater than 2, the time to reach infinity for the particle to roll down this potential all the way out to infinity is this. This is a finite number. Okay, so let me make sure that you understand what I've said. If I write down the classical equations of motion, I can calculate how long it takes for a particle to travel all the way out to infinity. This is the amount of time, okay? And this is a finite integral, and this is the exact answer. Okay, this is how long it takes for the particle to go to infinity. So if the starting energy of the particle is E, this is the exact amount of time for the particle to travel off to infinity. And now I'm going to ask you a question. If it takes a finite amount of time for the particle to go to infinity, where is the particle at t plus 1? Okay, and I'm going to let you think about this during the break, because this is a really hard problem. And it's a problem that's so hard that you can't solve this problem using real calculus. You have to use complex calculus. Okay, so again, let me just say what the problem is. Take this Hamiltonian with an upside down potential. Study this Hamiltonian, not quantum mechanically, just classically, and ask how much time does it take for the particle to roll down this hill and to travel all the way out to infinity? How much time does it take? And the exact answer is this. That's how much time it takes. Okay, that's a finite number. So it takes this many seconds to go off to infinity. So the question is, if it takes t seconds to go off to infinity, where is the particle at t plus 1? And if you can answer that question, you understand PT symmetry. And that's what I'm going to talk about when you come back. Okay? Do you all understand the question? I hope so. Think about it during the break.
Okay, I think let's take a break first and then we'll come back. at 11:10.
Professor Bender, now can I make a short comment for this two-box analogy?
Wait, just a second. Say it. I'm not quite able to.
Comments regarding to your two-box analogy for these PT symmetric systems. The two boxes draw. I think for that description, you also need to specify the reference frame for observing the physics, right? For example, if I
no. I'm not talking about relativistic quantum mechanics. I'm talking about non-relativistic quantum mechanics. I don't have to talk about a frame of reference. I'm just standing in my laboratory and I'm looking at this particle rolling down this hill, okay? And asking how long does it take for the particle to go to infinity?
Yeah,
okay, this is not relativistic.
No, I'm not talking about this problem. It's the previous point regarding to your optical fibers or two boxes systems.
Oh yeah, okay.
Yeah, I'm not talking about the last question.
Okay.
Yeah, I was saying that in your description, you are taking a reference plane at rest.
No. This is just optics in a laboratory. I mean, this has nothing to do with the reference frame. I don't know what you're talking about.
Yeah.
We are not talking about special relativity or anything like that. This is classical physics.
Yes.
There's nothing moving fast except light. But it doesn't matter that light happens to travel rapidly. We could do this with something that's traveling slowly. When light is traveling through a fiber, it doesn't travel at the speed of light. It travels very slowly.
No, I didn't talk about the special relativity at all.
But you're talking about a frame of reference. What do you mean by a frame of? I'm just standing there. I'm just standing there looking at my experiment. My experiment is not moving fast.
Yes, I'm saying when you describe that phenomena as a dynamical stabilities.
Yes.
That is, you have a balance between incoming and outgoing flows.
Yes, that's right.
That's what you mean by dynamical stability, right?
Yes, that's right.
Okay.
Because the system is not static, it's moving.
Yes.
However,
so
it
that's
remains, it is, the parts of the system are moving, but the system is not changing.
Yes, that's what I'm saying. But if I were taking the observer, which is in the co-moving frame with the fluid, then I would.
What do you mean by a co-moving frame? What? I mean,
in that frame, I would see a static equilibrium. That's what I'm saying.
Sure.
Yeah. So what?
I don't see the point. So what? I mean, if it's true, if I sit on a river and I look at the water, if I put a boat in the river and I look at the water, I don't see the water moving. So what?
So what I'm saying is that if you want to identify the dynamical equilibriums, you should specify the reference frame. That's only common.
Yeah. So the reference frame is clear. The reference frame is the laboratory. I am standing in my laboratory and I'm looking at stuff going in and I'm looking at stuff going out.
Yes.
Okay. And that is what I see in my laboratory.
Yes.
Okay. True. So if you like, you can call that a frame of reference, but we're not talking about relativity here. I mean, this is a trivial point. I mean, if I'm looking at you, I don't have to talk about which frame of reference I'm in, unless I'm talking about relativity. And I'm not talking about relativistic quantum mechanics here. I'm only talking about non-relativistic, which means that we don't have to worry about frames of reference. We understand what it means to stand in a laboratory and do an experiment. Okay, I mean, I can look down at a radio set and watch it work. Or I can look at a ping pong table and watch the ping pong ball going back and forth. And I don't have to think of myself as sitting on top of a ping pong ball. That's crazy. I'm just watching a ping pong game. Okay.
Mhm.
So during the discussion about this question, I think maybe the point is that if I just write down a non-Hermitian matrix and did not specify what is the reference state, it is not a well-defined problem. Can I understand it in this way?
No, it's a well-defined problem. If I write down a Hamiltonian.
I mean, I write down the Hamiltonian. If I don't know what is the basis, it can be anything, right? Like if I just write down the matrix, I don't know what is the first state, what is the second state. I cannot even distinguish it with the conventional Hilbert space one.
I don't understand what you're saying. Are you saying that if you write down a 2x2 matrix, you don't know how to calculate
for example,
the eigenvalue?
The 2x2 matrix that you mentioned, the box A plus BI and A minus BI, right? So for that case, the basis is very specific. We have a box where with water flow in and a box with water flow out, right? But if I'm writing out something that's kind of, I don't know, just the matrix, and I did not specify what is the corresponding basis, that would lead to a fact that it could be a state, maybe, I don't know, some photon coming in and some photon coming out. So if I did not specify the system, then
but are you telling me that I don't know how to write down a Hamiltonian? I mean, when you say basis, I think you mean that P is 1 over I d by dx.
Mm-hmm.
Okay, shall we agree that the meaning of P is 1 over I d by dx? So now I'm in a coordinate space basis. Yes. Okay, and I have two operators. One of them is x, and one of them is 1 over I d by dx. And the commutation relation of x with p is I.
Mm-hmm.
Okay, and I can calculate the eigenvalues of that matrix, and this has nothing to do with a frame of reference.
Yeah,
and that's why I don't understand what you're saying.
I see. So,
I'm not saying anything more complicated than undergraduate quantum mechanics.
Yeah, I think I'm overcomplicating things. What I have in mind is, like, for example, if I have a spin, like a finite dimensional Hilbert space, like quantum spin, and maybe I have, I don't know, thermodynamic, many of them, I can still write down a matrix, which is infinite dimension, and the matrix element will have completely different meaning. But if I did not specify that, I just have a matrix, then the interpretation could be dangerous. That's what I'm trying to say.
Okay. Yeah. What you're saying to me in simple ways, what you're saying to me is that if you make a very complicated problem, it can be very complicated.
Yeah, to some extent. So that's why
I mean, that's all I hear you saying.
Yeah.
You're saying if I make this into I mean, today I'm talking to you about one-dimensional quantum mechanics. I'm not talking about quantum mechanics in an infinite number of dimensions. I'm not talking about quantum statistical mechanics, and I'm not talking to you about quantum field theory. I'm just talking to you about one-dimensional quantum mechanics, and therefore we don't have to ask very complicated questions. If you would like to talk about complicated questions, that is where the research is being done on PT symmetry, because it can be very, very complicated.
I see. So maybe I can use this chance to ask. So the generalization for this non-Hermitian quantum mechanics, if I want to generalize it to many body system, is this a frontier of the research at this stage? Because I'm just not familiar with the situation.
Oh, absolutely. I mean, if you are interested in generalizing this to d-dimensional problems, where d can even be infinity, now you are doing research. And this is where people are doing publishable papers right now. I mean, there are papers every day on PT symmetry, and people are thinking about PT symmetric quantum statistical mechanics and PT symmetric quantum field theory.
I see.
And these are open questions, and I am not, I mean, today it's much, given that this is a summer school, I am not going to talk to you about, quantum field theory because I assume that the students, I don't know if maybe some of the students know quantum field theory, but this is much more, it's very interesting and very complicated. And, quantum field theory and quantum statistical mechanics are very complicated subjects. And I'm only talking to you about one-dimensional systems. That's all.
I see. So how about maybe something like entanglement? Is it also well established, or it is
no? In fact, the question of entanglement in a PT symmetric quantum field theory, there have been some papers written on it. It is an extremely interesting question, and I invite you to work on it. I mean, so PT symmetric quantum field theories, if you study issues like entanglement, that would be this is a research level paper, and I hope you work on it because this is very interesting. And the answer is not going to be trivial. It's going to be very interesting.
I see. So it is not yet answered, or at least not yet completed.
There is no, so far there have been papers written on PT symmetric entanglement. And as far as I know, they have been mostly wrong.
Okay.
So the warning is be very careful, because if you read a paper on the issue of entanglement for PT symmetric Hamiltonians, the worry is that you will you must be very, very careful, because people have made many mistakes and have made assumptions that are not valid. So
I see.
So one must be careful.
I see. Yeah, maybe I should ask this question maybe offline or something, because I think that's a very interesting subject, and I have shared the same feeling with you. It is really subtle, and one needs to be extremely careful about what condition can be used and what properties should not be used.
You must be very careful of your assumptions. You must really, really think hard about it, because this is very non-trivial. I mean, these are very, very difficult questions, but I hope you work on it, because this is very interesting.
I see. Thank you very much.
Yeah, it's about time for us to move on to the final part. So, Professor Fender, do you need a short break, or we can just continue?
Okay, shall I begin now?
Okay, yeah, please.
Okay, so I'm going to begin now. So I hope you understand this puzzle. What I've said to you is that that if we have a upside down PT symmetric minus x to the 4 potential, this is a hill. Okay, I mean, I want to make sure that you understand what I'm saying. Just a minute. Okay, this is a hill. I put a ball on top of the hill. Okay, so here's a ball on top of the hill, and I give it a push, and the ball rolls down. The ball rolls down the hill. Okay, and it rolls all the way to infinity. And we don't worry about the speed of light. Okay, we're just doing classical mechanics. And we ask, how long does it take for the particle to reach infinity? And what you see is that it takes a finite amount of time to reach infinity. Okay, there's no question about that. It reaches infinity in finite time. And you know how to write down Newton's equation and solve it. Okay, this is first year undergraduate physics, very elementary problem. And this is the exact amount of time it takes for the ball to reach infinity if it begins with an energy E. Okay, and the question is, where does it go next? Where is that ball when the time is t plus 1? Where is that ball? Okay, so to explain to you what is going on, I'm going to first talk about the harmonic oscillator. I'm going to talk about what happens if you extend the harmonic oscillator into the complex plane. What I'm going to show you is that you don't know the answer to that problem unless you understand complex variables. Without complex variables, you cannot solve that problem. It's a very simple problem, okay? And we're going to begin by studying classical harmonic motion. So the very first topic, you know, when you go to college and you're a first-year undergraduate student, what do you study? In physics, you study the harmonic oscillator. And this is what you learn. You learn that if you have a particle on a spring, here's the particle goes back and forth. It goes all the way out to a turning point where the spring is stretched maximally. Then it stops and it turns around and it goes back again. And it goes to the other maximum point and it goes back and forth. So you have oscillating motion, okay? And what you learn about is classically allowed regions and classically forbidden region. So here's the particle on the real axis and it's going back and forth. And this is the classically allowed region. The particle cannot go here because if the particle were to the right of this turning point, okay, where is this turning point? The turning point is where p equals 0. So the turning point is where x is equal to the square root of e. Now, if x is bigger than the square root of e, then x squared is bigger than e. But if x squared is bigger than e, then p squared is negative. And p squared cannot be negative. So this is called the classically forbidden region, and this is the classically forbidden region here. And you all know that, and this is trivial, right? But, and in fact, if you need to explain this to somebody, this is the classically allowed region, and you can't see the classically forbidden region over here, okay? But we can ask, what about the classical harmonic oscillator in the complex plane? Okay, so we only taught, this is the complex plane now, and we were talking about the particle going back and forth between the turning points. If you have a particle in the classically forbidden region, remember I said this is where p squared is negative. But if p squared is negative, it says that p is pure imaginary. So the velocity of the particle is actually in the imaginary direction. So if you want to study the harmonic oscillator in the complex plane, the particle is allowed to be in the classically forbidden region, but it is going in the imaginary direction. Okay, let me go back. It's going in the imaginary direction. Okay, so where does it go? So it goes like this, and then it comes around like this, and it goes back to where it started. So the particle is in an orbit, and for the harmonic oscillator, this orbit is an ellipse. And in fact, the turning points are the foci of the ellipse. So the possible classical motions of the complex harmonic oscillator are not just back and forth on the real axis, but they go around and around in the complex plane, in an ellipse. That's what the classical motion is, okay? Now, if we put in this is with epsilon equals 0. Remember the epsilon, there's an ix to the epsilon, remember that. So if we set epsilon equals 1, we get p squared plus ix cubed. And here are the turning points, and the turning points have moved downward into the complex plane. And instead of the particle orbits being ellipses, these are transcendental functions. Okay, they're elliptical functions, but the particle goes in a closed orbit. So the particle goes back and forth between the turning points in the complex plane. But if it doesn't begin on a turning point, it goes around in an orbit. Okay, in fact, what we learn from this picture is that the particle is not really going back and forth. If you think about the harmonic oscillator in the complex plane, this motion back and forth is not really back and forth. It's a degenerate ellipse. The particle is going infinitesimally above the real axis. It goes around the turning point. It's turning. It's going around the turning point and going back infinitesimally below the real axis and going around the turning point and going like this. It's in a degenerate ellipse. Okay? Now, if you have a p squared minus x to the 4 theory, there are 4 turning points. And if you study this in the complex plane, the particle is going back and forth between the turning points. And then there are an infinite number of closed orbits that go around the turning points. These are not ellipses, they're deformed ellipses. Okay, and now we ask, what happens if you roll a particle down a hill and the hill is a minus x to the 4 hill? What happens to that particle? Okay, well, that means that although we understand what is going on in the complex plane, we must approach the real axis over here. What happens as we approach the real axis? Well, as you get closer and closer and closer to the real axis, the particle is traveling very close to the real axis, and then it goes all the way out around like this and comes back up to the origin. So as we approach the real axis, what happens? Well, the particle goes all the way off to infinity, and then it makes an enormous loop traveling infinitely fast. And it comes all the way back up the negative axis, right back to the origin again. That's what happens, okay? Now it turns out that by Cauchy's theorem, remember the time that it takes to go in an orbit is an integral. And Cauchy's theorem applies to integrals, and the time integral is the same for all orbits because of Cauchy's theorem in the complex plane. So the amount of time to go back and forth like this is the same as the amount of time to go around like this, or like this, or like this. So what happens is the particle travels down the real axis in finite time. It then travels infinitely fast around to minus infinity over here and travels back to the origin. But the particle is traveling slowly near the origin and very fast when it's far from the origin. So the particle spends almost all of its time very, very close to the origin. So it is in a dynamical bound state. It's not in a static bound state, it's in a dynamical bound state. Okay? So if you ask what is the probability of finding this particle, it is most probable to find the classical particle near the origin, and it's very unlikely to find the particle very far from the origin because it's traveling very, very fast. So in fact, the particle spends almost all of its time very, very close to the origin. This is a sharply peaked probability distribution. So the particle is in a static is not in a static bound state, it's in a dynamical bound state. Okay, so remember, PT symmetry refers to dynamical stability, not static stability. So the particle is not balanced on top of the hill, but rather it spends all of its time, almost all of its time, very, very close to the origin. Okay, so again, what is the particle doing? It's going very, very slowly here. This is where the particle is most probable to be found, and then it goes whizzing around, comes back up the negative axis, back to the origin. Okay, so a system with static instability becomes dynamically stable in the complex domain. And this is something that nobody ever noticed before, that if you go into the complex plane, you can have dynamic stability, not static stability, but dynamic stability. And that's the reason why we can have stable quantum bound states, okay? So the instability, the static instability at x equals 0 is tamed. Complex mathematics helps you to tame instabilities. And what you see is that physical systems that seem to be unstable can become stable in the complex domain. Okay, so there are lots of examples of dynamically stable systems. For example, when you ride a bicycle or when you have a top, okay, spinning top, that spinning top is dynamically stable. It's not statically stable. If you stop, if you are not rolling forward on your bicycle, if you just stop, you fall down. But if you're moving, you stand up. So you're stable when you're moving. And that is what is happening here in the complex plane. Okay, so why is this true? Well, when you extend the real numbers to the complex numbers, nothing changes except for one single thing. When you go to the complex numbers, you can't say greater than or less than. If you have two complex numbers, you can, A and B, you can't say A is bigger than B or A is smaller than B. Can't say that. Okay? So when you say a physical system is unstable, what you mean is that it doesn't have a ground state. It can fall down. Okay? But when you say the system is unbound, the energy is unbounded below, you are using a symbol like this. And when you're talking about complex numbers, you cannot use that symbol. So physical systems that look unstable may not be unstable, like bicycles and tops. Okay? Now, I'm going to give you a proof that the quantum, that this Hamiltonian has real positive eigenvalues. Okay? So this is a very simple proof. It's freshman calculus, nothing more complicated than calculus. And this is the only case, the only non-trivial case I know where I can actually prove it to you in 2 pages. Okay, so are you ready? I'm going to show you a proof that, not just a classical proof, I'm going to talk about the quantum system. I'm going to show you that this quantum Hamiltonian has eigenvalues that are real and positive. Okay, even though this is an upside down potential. Okay, so this is the Schrodinger equation. And you remember that we require that the boundary conditions are that the eigenfunctions vanish in this direction, and they have to vanish in this direction in the complex plane. And what I'm going to do is take a particular curve, and I'm going to parametrize this curve in the complex plane. So I'm going to say, let x be given by this expression, that this is this curve, where y is a real number. Okay, so y goes from -infinity to infinity, and as y goes from -infinity to infinity, x comes up here and goes down here. So instead of writing the Schrodinger equation in terms of x, I'm going to write it in terms of y, and it's a mess. It's kind of complicated. Okay? But don't worry about that because that's just algebra. Okay? Now I'm going to take this equation and I'm going to take the Fourier transform. Okay? If I take the Fourier transform of this equation, I get this equation. And I simplify this equation, and this is what I get. Okay? And next, what I'm going to do is you notice this equation here has a 2 derivative term, and a 1 derivative term, and a no derivative term. Okay? And I'm going to do a simple transformation to get rid of this 1 derivative term. And the transformation is just this. I'm going to replace the dependent variable by this expression times another function, where this expression is over here. So this is just algebra. So now I get an equation that only has a second derivative term and a no derivative term. And this is a Schrodinger equation. Okay, this is a Schrodinger equation. And if I rescale the independent variable, I write it like this. This is what I get. This is the time independent Schrodinger equation for, notice, a positive quartic potential. So do you understand what I'm saying? We began with a negative quartic potential, and just by changing variables, I end up with a Schrodinger equation that has a positive quartic potential and also a linear potential. Now, the linear potential is negative, but I don't care about that because a quartic potential is much bigger than a linear potential. So the potential is a rising potential, and it has a positive spectrum. And that's the proof. Okay? So in other words, the Hamiltonian for this new Schrodinger equation is this, and you notice this Hamiltonian is p squared plus z to the 4, and then a linear term. So this is a rising potential. You notice what we did. We began with this potential, which is an upside down quartic potential, and we ended up with this potential, which is a positive quartic potential, and you know that the eigenvalues for a positive quartic potential are positive eigenvalues. Why are the eigenvalues positive? Because these are stable states, and they are stable states at the classical level and stable states at the quantum level. And this is really beautiful. I mean, this is one of the most beautiful things I've ever seen in my life. Okay, because I'm showing you something that's absolutely amazing. If you roll off to infinity, you are not gone. You actually spend all of your time at the origin, okay, in a bound state. You do not escape to infinity. You do not stay at infinity. So if you ask, where is the particle at t plus 1, it's back near the origin. That's where it is, okay? So the only thing is, let me show you this again. You notice that this term is proportional to h bar. And if you know something about quantum field theory, people talk about anomalies. You notice that this new Hamiltonian contains h bar explicitly. Okay? It contains h bar explicitly. And therefore, this is called an anomaly. And what this is a parity anomaly. This is the remnant of the PT symmetry. The parity symmetry, because we did a Fourier transform, the parity symmetry is not at infinity, but rather it's at the origin. And this Z vanishes at the origin. So we have, by doing a Fourier transform, we've taken some very strange behavior at infinity and moved it down to the origin, but it's proportional to h bar. And this is called a parity anomaly. Okay, so this upside down potential has exactly the same eigenvalues, exactly, as this potential, and this potential is a conventional right side up potential. This is Hermitian. Okay, this is Hermitian. It has real energy levels, and these real energy levels equal these because it is the same E. E has never changed. So in the calculation I showed you, I began with an E for the upside down potential. And when I finished the calculation, there's E for the right side up potential. E for one potential is the same as E for the other potential. So it's amazing that what you think is bound states, these are not, so you think of these as unstable states, but they're not unstable. They are bound states, even though we have an upside down potential, and that's amazing, okay? And if you look at the classical motion, if we take the original potential and ask, how does this particle travel in the complex plane? It goes around like this, okay? And if you ask, how does a particle travel in this potential? It goes around like this, okay? But it's very interesting. Although they have the same quantum energies exactly, all of the quantum energies of one potential are equal to all of the quantized energies of the other potential. At the classical level, notice we have an H bar, but in classical mechanics, H bar is 0. So therefore, at the classical level, where I set H bar equal to 0, these two orbits are not the same. The period of the orbits is not the same. And if you set H bar equal to 0, it takes a different amount of time for the orbit to close. So the orbit wants to close, but it didn't have enough time to close. Okay, so these two systems are exactly the same at the quantum level, but they differ at the classical level, which is very, very, very interesting. So let me explain intuitively how you can understand this. So imagine you have a potential that looks like a staircase. Okay, you understand quantum mechanics, and you know that if I have a particle at the top of this staircase, what will happen to a wave function? This is a rabbit. What happens if I write down the wave function for a rabbit? Well, the wave function spreads, right? And when it reaches this point, it reflects, it diffracts, okay? And part of the wave function goes back and part of it goes forward. Then the wave function continues to spread and part of it goes backward and part of it goes forward. And if you arrange the staircase right, a little bit diffracts back, more diffracts back, more. And in fact, the wave function never reaches infinity. So although the classical rabbit is hopping all the way down to infinity, a quantum rabbit never gets to infinity because it keeps getting diffracted at each point. And what I have been talking about is the continuum version of this staircase. Okay, so this is an intuitive way to understand the nature of stability. Okay, so this is what I've told you. I'm going to summarize what I've told you so far. If we have a right side up potential, you have a bound state in this potential. If I make it an upside down potential, like this, then you learn in your conventional quantum mechanics course that this particle now is unstable and it tunnels out to infinity, right? That's what you learn in your quantum mechanics course. And this is not an equilibrium situation, okay? Because the particle in this potential well is gradually disappearing and the particle is traveling out to infinity. But what we are talking about is particles, is a system with gain and loss. So the particle travels out to infinity and comes back up from minus infinity, out to infinity, around and back up from minus infinity. So this is the gain and this is the loss, and they are in balance. And therefore the state in the middle is not going down and it's not going up. It's in dynamic equilibrium. And that is what is happening in a PT symmetric Hamiltonian. We have dynamic equilibrium. Okay? And I hope you understand what I'm saying. This is not trivial. This is really very, very, very subtle. Okay? But we have a balanced loss and gain. And we have that balanced loss and gain at the classical level and at the quantum level. Okay? It happens classically and quantum mechanically. Okay? So this is called unidirectional scattering. We first, I wrote a paper with a guy in India and Michael Berry, who's known for the Berry phase, on reflectionless potentials, upside down potentials with PT symmetry. I wrote another paper with a colleague on this. This reflectionless scattering was observed in PT symmetric optical scattering systems. And this is just one paper where they observe this, okay? And I mentioned at the beginning of my talk that we just wrote a physical review letter on cold atom scattering off a minus x to the 4 potential or minus x to the p potential on the real axis, okay? And you can read this paper. This is just a few weeks old, where we should be able to observe those energy levels in a simple cold atom scattering experiment where you have loss and gain, balanced loss and gain. Okay? So now I have about maybe 15 minutes, and I'm going to show you some. So I should ask you, that is a very basic introduction to PT symmetry. And I thought that you might be interested in some more advanced problems just involving simple quantum mechanics. Shall I tell you about that?
Yes, please.
Okay, so I will go faster now, and maybe you will have a feeling for some of the interesting things you can do with studies of PT symmetry, just one-dimensional PT symmetry, okay? So for example, instead of an x to the 4 Hamiltonian, let's take an x to the 6 Hamiltonian. Now, you know that if you set this equal to E and you calculate the turning points are here. There are 6 turning points because the turning points satisfy the equation x to the 6 equals E, right? So in the complex plane, we have 6 turning points. And if you ask, how do classical particles move? Well, there's the one example you know from your elementary physics course is that the particle can roll back and forth, because this is an x to the 6 potential well. It can just roll back and forth in the potential well and go back and forth like this. And if you ask, how does the particle move in the complex plane? It goes around like this. Okay? But there are these 2 turning points and these 2 turning points. Okay? So if you start a particle here, it goes back and forth between this pair of turning points. And if you don't go back and forth, it goes around and around. Okay, around and around. And in fact, there are 3 regions of classical orbits. There's this region here, there's this region here, and there's this region here. There are 3 types of classical orbits. This is classical motion, okay? And these orbits fill the complex plane, okay? But what happens if we take the energy of the particle not to be real? We take it to be slightly complex, okay? So the energy is not real. It has a slight complex part to it. What happens now if the energy is complex? Well, the particle, this is a plot of the particle. It's a little bit hard to see this, but the particle starts over here and it goes around and around, and it comes, instead of 3 separate regions of classical orbits, the particle goes around and around, it goes into another region, it leaves that region, goes into another region, and it jumps from region to region. So it is tunneling. So in this picture here, these orbits are isolated orbits. They cannot mix. But if the energy is slightly complex, now the classical particle can tunnel from this region to this region. Okay? So we see a tunneling classical particle. Tunneling from classical region to region. And in fact, what we see is deterministic random behavior. Here is the classical particle. It is in one region, then it jumps to another region, then it jumps to this region, then it jumps back up to this region, and it jumps, and it goes back and forth in a chaotic fashion. So we have deterministic classical random behavior, okay? And here is the same example for an x to the 10 potential. And this is very interesting because we have classical motion in this region, classical motion in this pair of regions, classical motion here, classical motion here, classical motion here. And at the quantum level, we have, this is the standard Hermitian quantum mechanics problem. This is a PT symmetric quantum mechanics problem. And here's a different PT symmetric quantum mechanics problem. You notice left-right symmetry of the turning points. And what you see is that the energy levels in the conventional problem are these numbers. These are the energy levels. In this pair of turning points, we have bigger energy levels. And in this pair of turning points, we have an even bigger energy levels. And this is very interesting because for the same Hamiltonian, p squared plus x to the 10, we have 3 different spectra. And if you think about the real world, you know, there are 3 kinds of leptons. Okay, 3 kinds of leptons. They have almost identical properties, except that the masses of the leptons get bigger and bigger and bigger. So it is possible that when you talk about the electron and then the muon and then the tau particle, which is much heavier than the muon, and the muon is much heavier than the electron, what you could be seeing is the complex plane. Exactly the same Hamiltonian for the electron. When you study it in the complex plane, it has higher energy levels and a bigger mass. Okay, and if the energy is slightly complex, you can tunnel back and forth. And that's what happens in real life. Given a tau particle, it can decay into a mu particle. Okay, and the mu particle can tunnel, it can decay into an electron. Okay, so what we're seeing is the possibility of explaining the real world in terms of the complex plane. Okay, which is really interesting. Okay, and I'm going to show you some of the orbits. Okay, so here is an example of a Hamiltonian. This Hamiltonian has an x to the 4 rising potential and has a negative quadratic potential So the potential looks like this, okay? So what is the classical motion? So if you take the energy to be -1, so this is -1 over here, what does the particle do? It goes back and forth, okay? If you put a particle in this well, it goes back and forth. So it goes back and forth here, okay? But if you put a particle in the complex plane, it goes around and around. But notice that this particle here cannot cross to here. You cannot tunnel. A classical particle is not allowed to tunnel from this well to this well, even in the complex plane. So all of these orbits stay to the right, and all of these orbits stay to the left. And no orbit can go from this side to this side, okay? So it can't do that on the real axis, and it cannot do that in the complex plane. But if we make the energy complex, now the particle spirals around, it crosses over here to this, it goes into this well, it comes back out again. So the particle can tunnel back and forth through the complex plane. And that's very interesting because if you studied tunneling in quantum mechanics, while the particle is tunneling, where is it? And you don't know where the particle is when it's in the process of tunneling. And that's because the particle is in the complex plane. You cannot say where it is, it's simply traveling through the complex plane. Okay, and that is exactly what is happening here. So if you give the particle a little bit of complex energy, it tunnels back and forth. And what is really interesting is you can ask, how long does it stay in this well until it tunnels to this well? Okay, and it turns out that if you multiply the imaginary part of the energy times the average time spent in a well, it's a constant. And so although this is classical physics, we see a time energy uncertainty principle in classical physics, which is really interesting. So this shows you that complex mathematics is really, really interesting, okay? And furthermore, you can even see resonant tunneling. So if you're very clever, you could choose exactly this number for the imaginary part of the energy. And if you do, the particle starts here, it goes around, and it goes right into the other well. And this is resonant tunneling. It doesn't take forever to go into this well. It doesn't do random behavior. It goes directly to this well and bounces back again. And it goes back and forth from well to well as if there is no gateway. There's no problem about going back and forth. So this is resonant tunneling at the classical level. This is an even more complicated resonant tunneling. And I want you to see something really interesting. How does the particle go from this well, the right well, to the left well? Okay, well, the blue particle starts here at this turning point. It goes around and around and around and around and around, and it ends at the turning point in the other well. Okay, but what does the red particle do? The red particle goes around and around and around, and it goes faster and faster, and it goes off to a minus I infinity. And then it comes back down from plus I infinity, and it goes around and around and around and ends over here. So I want you to notice that the red particle goes from the right well to the left well, but it never crosses x equals 0. It never crosses this line. So you can go from one side of the universe to the other without going through the middle of the universe, because what the particle is doing is going off to infinity, minus I infinity, and coming back from plus I infinity, which is really amazing, okay? Okay, so you can see how much fun you can have doing complex quantum mechanics and complex classical mechanics, okay? And this is a really fancy example of that kind of a plot. Okay, now, let me see. I'm not going to talk about this, but so this is, you know, you have to give some sort of conclusion, and this is an overview of my talk so far, and I noticed that somebody is sleeping back here. This is me standing talking to you, and somebody has fallen asleep. So I promised to say something about the theory of the model, to talk about the inner product and so on. There are quite a few slides left. So you can ask, is this quantum mechanics? You can ask, can you find an inner product that is positive definite? Okay, the eigenfunctions must be orthonormal with respect to this inner product, and you have to show that time evolution is unitary. Okay, and I have a feeling it's getting late for you, and I probably shouldn't explain it to you, but maybe I will just say 1 or 2 words about it if you would like. I should ask you, would you like me to just summarize what this is saying?
Yes. Please.
Yes, please.
Okay, so I will try to say something in just about 2 or 3 minutes, just to give you a feeling for why what I've been talking about when I talk about complex quantum mechanics, why this is real quantum mechanics, okay? I'll try to explain that to you. And in fact, what I'm going to do is, I have slides, but there are too many slides here. And so what I'm going to do is, I'm just going to do this on a piece of paper, and I'm going to show you, I'm going to just write some equations down and show them to you. Is that okay?
Yes. Yes.
Okay, so I'm going to stop sharing my screen, and can you see me better? Can you see the picture of me better?
Yes.
Okay, so this is the theory of PT symmetric quantum mechanics, and what I'm going to explain to you is this. In PT symmetric quantum mechanics, what you know is that the Hamiltonian commutes with the PT operator. If this is true, if the Hamiltonian commutes with the PT operator, that means that you have PT symmetric quantum mechanics, okay? Now, you remember that I said to you that there is a region of broken PT symmetry and a region of unbroken PT symmetry. In the region of unbroken PT symmetry, the energies are real, okay? But there is something else that is really remarkable, and that it took me a long time to understand, okay? Many years before I understood this point. If you are in a region of unbroken PT symmetry, where the energy, all of the energy levels are real, the Hamiltonian has a secret symmetry that I didn't know about for several years, okay? What that means is that there is another operator that commutes with the Hamiltonian, and I call this operator C, okay? So the C operator also commutes with the Hamiltonian, okay? So I have to say this again. If you have a Hamiltonian that is PT symmetric, which means that PT commutes with the Hamiltonian, sometimes the energies are all real, and sometimes the energies are not all real. They may be complex, okay? Now, if you have a situation where all the energy levels are real, it means you're in a region of unbroken PT symmetry. And if you are, that Hamiltonian has another symmetry that guarantees that all the eigenvalues are real. That symmetry, to express that symmetry, there's a new operator that we don't know about. And that operator is called C, okay? And that operator C, just like PT, C commutes with the Hamiltonian, okay? Now, the whole key to understanding PT symmetry is to understand that C operator, okay? So the C operator has three properties, okay? The first property is, number one, is that C commutes with the Hamiltonian, okay? Number one, C commutes with the Hamiltonian, okay? Number two, C commutes with PT. So the operator C is itself PT symmetric because C commutes with PT. That's the second equation. That's equation number two. Okay. And equation number three, this is the last equation. Equation number three is that C is a reflection operator. That is, C squared equals 1. Okay, C squared equals 1. Now, these are three equations. C commutes with the Hamiltonian, C commutes with PT, and C squared is 1. Now, those are three simultaneous equations. And if you want to know what the C operator is, you have to solve those three simultaneous equations to calculate the C operator, okay? That's not easy. It looks like it's going to be easy, but it's not easy. However, you can do it approximately, and you can calculate the C operator, okay? So imagine you have now calculated the C operator. What do you do with it? Okay, and the answer is you construct the inner product. Okay, and how do you define the inner product? Well, you take a state. This is a state, let's call it psi. This is a state in the Hilbert space, okay? What is the inner product? Well, you know that this is called a ket, okay? The inner product looks like this. In conventional quantum mechanics, that's the inner product, okay? And what is this bra over here? That is psi star, okay? That is not psi star, but psi dagger. In other words, if you have a state, you dot it into its Hermitian conjugate, and that is the inner product, okay? In PT symmetric quantum mechanics, you construct the CPT operator, okay? So if you have a state in your Hilbert space and you want to know what the inner product is, you take that state and you multiply it by CPT. Instead of dagger, you use CPT. And the inner product is what you get if you dot the CPT state into the state. And that inner product is a positive inner product, And that is the probability that you need to measure when you do an experiment. That's the probability of the outcome of your experiment. And that probability is a positive definite quantity. Okay? So that is the general, that's the complex. So now you understand, that is the complex generalization of conventional Hermitian quantum mechanics. And what you need to do is to construct the CPT inner product. And this is very much like the famous CPT theorem in particle physics. Okay, it has a very strong analogy if you know about the CPT theorem. Okay, and so the CPT inner product exhibits unitarity, that is conservation of probability, and the probability is a positive number. And so everything I have been talking to you about today is not just mathematics, it is physics, because that is the thing that distinguishes quantum mechanics from some other silly theory. Okay, in quantum mechanics, you have an experiment, and when you make a measurement, you measure a probability, and that probability must be positive. And in PT symmetric quantum mechanics, there is a probability. And the only difference is that in conventional quantum mechanics, you already know what the definition is of an inner product. It's just psi dagger psi. Okay? But in PT symmetric quantum mechanics, you don't know what the inner product is until you calculate the C operator, which is not trivial. But when you calculate the C operator, it's not psi dagger psi, it's psi CPT psi. Okay? So what I'm telling you is that the Hamiltonian determines its own inner product. You don't know the inner product until you solve for the C operator. And that takes work. You have to do that. But that's how the theory of PT symmetric quantum mechanics works. Okay, so you can read about it. I showed you this book. There's a whole chapter on the C operator and how to calculate the C operator. Okay, and you can learn about the inner product. And this is the rigorous quantum mechanical interpretation of what I've been telling you. I've been telling you a lot about differential equations and energy levels and so on, classical orbits and so on. But in fact, this is a true theory of quantum mechanics because we have the theoretical underpinning of the theory, okay? We have unitarity, we have an inner product, we have a positive inner product, and therefore this is an exact, strict, rigorous theory of quantum mechanics. Okay, so I hope you found this interesting. Thank you very much for listening. And if you have more questions, I'm very happy to try to answer them.
Hello, Professor Bender. Thank you very much for this wonderful talk, and we all enjoy your lectures very much. Here I have two questions. First one is the distinction between the dynamical equilibrium and say steady state non-equilibrium.
Steady state.
Steady state non-equilibrium. Say
steady state. So you're saying steady state non-equilibrium?
Non-equilibrium, where you have alternate dots subject to the voltage bias, where you have something, say, charge currents flowing from one side to another. So very much like the boxes that you mentioned, that you put something in, and in one box and another, box that something is going out. So, but these two situations are different, right? So one is your case where the dynamical equilibrium. Another is indeed we have say a dissipative.
Sure. So I'm not sure I completely understand what you want to know. I mean, if so, we understand what it means to have a steady state. The steady state means time independent. Okay. If things are flowing, then they're not time independent, right? So if you have a pot of water and you're pouring water in and water is coming out at the same rate, the total amount of water in the pot is constant in time. So that's what I mean by a dynamical equilibrium, because the total amount of water in the pot doesn't change in time. But it is true that this is not a steady state because water is going in through one hole and it's going out through another hole. And what that means is that water inside of the system is constantly flowing to equilibrate the system, right? Because, if you have water coming in one side, let me draw a picture, okay? So this is a system over here, okay?
Yes.
Now I'm going to drill a hole in one side and I'm going to drill a hole in the other side. And I'm going to have water going in. The water is going to go in this side and it's going to go out this side. So therefore, this is not steady because things are moving. I mean, the water that is coming in this side has to move slowly to get to the other side in order to go out. But if it can do that, okay, if the water can flow fast enough so that the total amount of water in this box does not get bigger or smaller, then I say the system is in dynamical equilibrium because the total amount of water in the box is constant in time. However, it is not a static system because water is going in, it's going. If something is going, it's not static, okay? And water is going out. So if it's going, it's not static. So it means that the system is in equilibrium, but the equilibrium is not static, it's dynamic equilibrium. It is exactly the same as if you have a top or a gyroscope. If you have a gyroscope, what does the gyroscope do? It is spinning and it is going around, it is nutating like this, and it is going around and around, right? But it doesn't fall down. So it is in a dynamic equilibrium because it does not fall down. If the if this gyroscope stops spinning, it falls down.
Yeah.
Okay. So you understand the distinction that I'm.
So here's my second question, which is related to the first one. So
yeah,
your very new so the counterintuitive results based on this complex span. Does it rely to the fact that we need to create a dynamical environment, such as the spinning top or something which flows this system so that to stabilize your the bound state in this dynamical equilibrium state, which means that if I don't inject, say, energy or something in your system, which means that there's nothing in, getting injected in the system, nothing is getting out, and your results are not very easily to be observed. In other words, do we need to create the dynamical environments in a real experimental setup to observe this new phenomenon?
I think what you're asking is, I'm not sure, I couldn't hear all of the things that you said, but I think you're asking, what is the nature of a laboratory experiment in which we are looking at dynamical equilibrium? Is that your question?
Yeah, more or less, which are relevant for your theoretical results, right? So,
right. So,
how to realize this in the lab so that you have a dynamical equilibrium.
Right. So I can give you a simple mechanical example, if you like, where you have energy going in and energy going out. It's very simple. Okay, would you like such an example?
Yes, please.
Okay, well, suppose you have a rope. So this is just a rope.
Yes, I can see that.
Okay, and it is under tension. So this rope is being pulled pretty tight. So I'm pulling it this way and I'm pulling it this way. Okay, and now I have a pendulum hanging from this rope, and it is swinging back and forth. Okay?
Okay.
And I have another pendulum also swinging from this rope. So there's a rope, we have a pendulum, and this pendulum is swinging back and forth, and another pendulum is swinging back and forth. Okay?
Yes.
Now, these pendula, if this pendulum is swinging, it eventually will make this pendulum start swinging, because these pendula are coupled through this rope. They're not independent. So if I give this pendulum a push and it starts swinging, eventually the other pendulum will start swinging. Do you agree?
Yeah, I see your point. Thank you. This is exactly what I want to know. The real setup.
Now, well,
dynamical.
Okay.
Equilibrium.
Right. So what I'm going to do is I'm going to push this pendulum. Okay, so I will push it to make the pendulum swing, and I will put energy into the pendulum. Okay? But this pendulum, I will have this pendulum has friction. Okay?
Okay.
So energy is going into this pendulum because I'm giving it a push. But energy is going out of this pendulum because there's friction in this pendulum. Let's say it's swinging in water, or there's friction in the connection to the rope or something, okay? So I have two pendula, and I push this pendulum, but this pendulum has friction. Okay, now that system, if there is a weak coupling between the pendula, what will happen? A very weak coupling. Well, because I'm pushing this pendulum, it swings higher and higher and higher, and it's getting bigger and bigger and bigger. It has more and more energy. Of course, it's losing some of the energy to this pendulum, but not very much. So the total energy in this pendulum is growing bigger and bigger and bigger, and the pendulum swings higher and higher and higher. Okay? Yeah. However, if the coupling of the pendula is pretty strong, then the energy from this pendulum can go into this pendulum. And so I put energy in this pendulum, I take it out of that pendulum, and the two pendula are swinging, and their amplitude of swing is constant.
I see.
Okay, so this pendulum, the amplitude of a pendulum tells me how much energy there is in that pendulum. Okay, yeah. And if I adjust the flow of energy from the one pendulum to the other pendulum, I can put energy in this pendulum, I can take energy out of that pendulum, but the pendula are swinging at the same amplitude, and that amplitude is not changing. The two amplitudes do not have to be the same, but they're not changing. Okay, so one pendulum could have a big amplitude, the other pendulum could have a very small amplitude, but the amplitudes are not changing. If the amplitudes are not changing, then I would say the system is in dynamic equilibrium because nothing is changing. But of course, you're right when you say that it isn't static because energy is flowing. So that's not a static system, but I would call it dynamical equilibrium because the physics of the system is not changing. The pendulum amplitude is not increasing in time or decreasing in time.
Okay, thank you very much. I fully understood your
yeah, and so that is what we mean by a PT symmetric system. And in fact, I published a paper with a student where we actually built a pendulum and it behaved exactly like that, so that we could make a PT symmetric pendulum. So it's a very nice, simple system.
Thank you very much. Thank you.
Okay, take one more questions.
So let's go back to the upside down quartic potential. In such a case, is there also continuous spectrum in the system?
Is there also what?
Continuous spectrum, because
did you say continuous?
Yes.
Yeah. No. Though the upside down potential has an infinite. So if the potential is going down to minus infinity,
yes,
the potential. So let me draw a picture again. So what you are talking about is a potential. Let's see, I don't think you can see that. Let me just make it darker. Okay, so you are talking about a potential that looks like this.
Yes.
And we're talking about an infinite potential. So the potential goes all the way down. It goes all the way down to infinity.
Yes.
Okay. Now, what I have said is that there are eigenstates of this Hamiltonian. Okay, so the Hamiltonian is p squared minus x to the 4, for example.
Yes.
And what I'm telling you is that there is a spectrum of positive energies that looks like this. These are the energy levels, and they're all positive.
Yes.
There is no continuum spectrum. The energy levels are discrete, just exactly like the energy levels, say, of the harmonic oscillator. The harmonic oscillator has no continuum energy levels, and the energy levels of the upside down quartic potential, for example, there are an infinite number of different potentials. The energy levels of that Hamiltonian are also discrete. There's no continuum energy levels.
So there is no the so-called scattering states in such a system?
Well, that's okay. Now, if you want to talk about scattering states, of course, you can't do that. You can't do that with this potential because this potential goes all the way out to infinity. And if you're going to talk about scattering, you have to have particles coming in from infinity and going out to infinity,
yes.
Right?
Yes.
Okay. But that's not a problem. And in fact, I mentioned this physical review letter that I just wrote, okay? And in the physical review letter, we talk about something slightly different. We talk about this kind of potential. We have a potential that looks like this, but the potential does not go down to minus infinity. It just stops. Okay, so let's suppose we have a potential that looks like this.
Okay.
Okay, so now we could talk about scattering theory because when you go sufficiently far away from the potential is 0.
Okay.
Okay, so now there are a few bound states of the potential. Okay, and these bound states, so ordinarily, if you have a potential like this, what you know what you expect to happen, of course. What you expect to happen is that there will be an incident wave coming toward the potential, right? This is an incident wave. And what does happen? Normally, what do you expect to happen? What you expect to happen is that you will have a transmitted wave, okay, over here. This is the transmitted wave. Here's the incident wave, transmitted wave. And then you will have a small reflected wave that looks like this. So can you see that?
Yes, I can see that.
Right. So I hope there's enough light. So the incident wave is coming here. This is the transmitted wave. And then there's a small reflected wave. But as you vary the energy, you will find an energy where you have, at some energy level, you have a wave coming in like this, okay? And a wave going out and no reflected wave.
Okay.
That, at that energy, that is the PT symmetric energy.
I see.
Okay? That is to say, you have gain, you have loss, and that's it. And at that particular energy, that is one of the energy levels of the PT symmetric system. Okay, because you have gain, you have loss, and you have no reflected wave. So it's unidirectional propagation, no reflected wave. Not even an exponentially small reflected wave, okay? And that's how you measure with cold atoms, that is how you measure the PT symmetric spectrum. That's precisely how you measure it.
Thank you.
Okay?
So we'll just take one more question from online audience. Is there a question from online audience? Okay, I think it's getting pretty late, and so we would like to thank you, Professor Bender, for his very nice pedagogical and tell us about this exciting field. So let's thank Professor Bender again for his talk.
Okay. Thank you. I hope you work on this problem, and I hope you publish some papers. It's a very exciting field to work in.
Yes, we agree. Thank you very much.
Okay. Bye-bye.
Bye-bye. Good night.